To kick it off, to introduce myself, my name is Émile Le Chevrier. I have a very French last name, but I go very well with Émile, or however you want to pronounce it. Please just call me Émile. There's nothing formal needed here. I wore my jacket to impress you, but just call me Émile, please. I consider myself to be a pretty young guy. I wouldn't say I'm a young engineer anymore, because I had to count it up, and I've been in the industry for 11 years, so I've been working for 11 years, mostly based in the Netherlands, but always working for international companies, starting in oil and gas, and then transitioning into the valve industry, where I've been for 8 years already. So I've been with Ventil test equipment for 8 years. And I've had a few different roles. So I've had project management role, I've had a sales engineering role, I've had some business development, and now everything sort of came together. And if I have to describe what my job is today, is to basically come up with what we have to do in the future. So everything which you cannot buy from the book tends to cross my desk. So whether it's innovation, whether it's a strange question, whether it's something we want to automate, if it's a very particular use case, or if it's a problem from the market, I tend to get involved, and we try to innovate based on that. So you might know me. I've been doing some conference presentations. Some of the subjects may seem a little familiar, but you know, I think there's always a different angle that we can add every single time, so I hope it's interesting. I also participate in steering committees, so for instance for the valve world and for Virginia, we try to help make events in the valve industry a bit more wholesome, to bring new subjects and really talk about innovation. I'm also the lead for what Oscar mentioned, the forming gas project, so the introduction of a new tracer gas for fugitive emission testing, which was a project with Shell, but more about that later on. And I also get involved in standardization initiatives. Most recently, API 6D, NXM, some of you might know me from that. We contributed there because we feel it's our responsibility to participate and represent the process of testing in standards as well. All of that together, I like to say I'm subject matter expert for hydrogen. I'm the lead for engineered solutions, so anything non-standard. And I'm also the specialist when it comes to leak detection. So not just hydrostatic testing, but also leak detection equipment. I'm here today on behalf of Ventil Test Equipment, and if you don't know Ventil Test Equipment, it's a very reasonable thing, because we're not so big in Italy. But Ventil Test Equipment, as a manufacturer of test benches, has been around for more than decades. We've been around for a very long time, and we employ around 130 people worldwide, divided over 3 different manufacturing locations, which means that my headquarters is in the Netherlands, which is where I'm based, where we manufacture machines. We have our Center of Excellence, which is engineering, software development, and PLC engineering, and also a group of experts working in the valve industry. Then we have a location in Houston and in the Middle East, so essentially Dubai, UAE, and those are manufacturing sites as well. With that, we have more satellite offices, and we have partners, much like our partner who is here today, STC, kind enough to join us today, because we have a strategy where we have centers of excellence based in our manufacturing locations, and we have supporting people that do the work on the ground. So they are your first point of contact. So like I mentioned, it's all in the name, Ventil Test Equipment. We specialize only in manufacturing test benches. We do not provide the service of testing. We only manufacture equipment to test valves. And to give you an impression, in a normal year, we build around 300 test benches every single year, big and small. So our products are basically divided into 4 main segments, which is products for design validation. So it's things like cryogenic testing, it's fire safe testing, it's climate chambers, things like that. So very particular type of testing, which you don't do very often. The second is production testing for instance, valve manufacturers that produce a high volume of valves and they need to do FAT on the valve. So we have automated solutions for that. A big portion of our market also goes to repair and maintenance industry. So it's companies like Shell, Aramco, they have our machines in their workshops, but even the companies performing maintenance in the field, they tend to have our test equipment as well. And then finally, it mostly relates to pressure relief valves. We have solutions for what they call in situ testing, which means that you test the valve while it's still in the pipeline. Now, obviously, I'm not here to present to you today about our products, because I could spend a week talking about how fantastic our products are, but today I'd like to tell you a little bit more about what we feel is our responsibility in the market, and that is to innovate with the perspective that we have. So our mission, our company mission, is to contribute to safety in the industry, and a direct derivative of that is a test bench, because it's a quality control device, and we would like to think that with the input we get from all different players in the industry, that we can improve these test benches to a point that they automatically contribute to safety in operation. And this is one of the core things that we'd like to do. So this is our mission statement from our CEO, and this is exactly the reason why we're here. This is exactly the reason why we do this on a voluntary basis. So we don't get paid for this. We don't make money off of this, but we do have insights which could be very relevant. And to give you an impression of the things that we've done over this year, so for 2025, we have 3 main projects that we had throughout our project agenda. The first being to standardize on safety screens, because we know that on a global scale, there is a dozen of fatalities while pressure testing on a yearly basis. So it's people who are not properly protected from the dangers of pressure in untested objects, causing incidents, causing, in many cases, loss of life. So we set out to standardize safety screens, just to make sure that the decision for safety is easier. The second one, which will come back later on in the presentation, is what we call the concept of ultra, which is a new way of testing valves to reduce cycle time, to be more competitive in European countries. But again, I'll get back to that later on. And then finally, on the subject of hydrogen, we'd like to get involved to prepare our industry what it takes for the future of hydrogen valves. So what are the practical elements that we need to consider? What do we need to do to prepare ourselves for a big volume and perhaps even bigger valves? And how can we realistically achieve that without ruining our own business case? Because we can make everything very complicated, everything very expensive, but it means that we will never have a proper business case to get this off the ground. So these are 3 projects that we've worked on this year, and at least 2 of those, so ultra and hydrogen, they will come back in the presentation. Our schedule for today, this morning, I'd like to talk to you about automatic testing. So it's automation in valve test benches. So it means that until lunchtime we will talk about automation. And there will be a coffee break in between. So no worries if you're falling asleep. There's a good moment to recharge at least. Then we'll have lunch, and after lunch I will tell you about the Oil&gas project. And then afterwards, again, we'll have a short coffee break to recharge you again, and talk about something which is, in our opinion, relatively new, and that is testing at minus 250 degrees Celsius for liquid hydrogen applications. So I hope to keep you very interested today. And let's get started, because time flies, and well, I could be here all week, basically, talking about these things. It's what I do every day. It's passion. It's great. You put a coin in the jukebox and it starts playing music, right? So, automation for valve testing. So the perspective is we're talking about test benches. So consider that you're valve manufacturers, you're producing valves, you have to do FAT on your valve. So let me start with a statement. Do you agree with this? So automatic valve testing only makes sense if you produce hundreds of the same valve every single day. Who disagrees with that? So who thinks automation is a good tool anyways, even if you produce low number of valves? You can raise your hand. I won't ask any other questions. So everyone feels that automatic testing only makes sense if you produce mass production, basically. Hundreds, thousands of valves.
Frankly speaking, yes.
It only makes sense. Okay, it's an honest answer. I appreciate that, Oscar. And this is a stigma, right? This is the perception. Automation is expensive, we have to do many things, and there's many arguments why you should automate. In fact, I have a sheet, because what I did, I consider myself a young guy, so I asked ChatGPT, automation, why does it make sense, right? This is the way to go. This is how we get information. And I get all these arguments. So I can talk about efficiency, productivity, compliance, transparency, digitalization, and all of those words make perfect sense. Because you feel like, okay, sure, this is something I would like to pursue, but what does it mean for me? And what does it mean for a test bench? It's just too abstract. So with that statement in mind, what does automation mean? Well, to carry on this, I think that at least two of these are never really relevant. So again, this is something I got from the internet, ChatGPT, just generalized information. And I always feel that accuracy and speed, they don't go hand in hand with automation. Because if you buy a milling machine, CNC milling machine, or a lathe, it doesn't get more accurate. You can't get more accurate parts produced from that machine because it's automatic. No, it has a high grade of repeatability, but not necessarily accuracy. Machining by hand could still be more accurate. And it's the same argument with speed, especially for valve testing. Some things you cannot really speed up. So can a machine do something quicker than a human being can? If that human being has been doing it for decades, maybe all his life, all of his professional career, then maybe he is much quicker at it because he has feeling, he has experience. He can correct for things on the fly, and a machine cannot do that. So speed is a very poor argument for automation. All of the others, I would say, probably relevant in some short form or way. But do they really, really give you an argument to automate your valve test bench today? I don't think so. So let's bounce back a little bit. Because we're talking about automation, I could speak about this for days because it has many different aspects. So let's establish a small process to have a benchmark, to know what we're talking about. And let's consider a simple valve. So the standard is EN12266. Pretty much the basic valve that we know in the industry, right? You could argue, well, why not take an API 6A valve because it's much more elaborate. I quite simply said it's just more steps that I need to go through. It's just about establishing this is the benchmark for now. So let's take an EN12266 valve for the rest of the day. This is the benchmark process. And what do we have to do when it comes to testing? Again, keep it simple. If I look at the matrix for these standards, so on the left here, you see the requirement from EN12266, and on the right you can see API 598. So there's a few small differences, but the essence is always the same. There's a few different tests that I need to go through, and it's the minimum that I need to provide. And it's the same if you follow any API standard or any EN standard, ISO standard, because we always need to do the similar things, right? So it's strength, tightness of the seats, and then probably we need to do something with what they call the obturator, which is essentially operating the valve, open and close. So looking at definition, throughout the presentation I will be using the codes. So P10 basically means the shell strength. test. It's easy. I think everyone knows this, right? It's a hydrostatic test. Pressure is 1.5 times working pressure. There's a test time specified. It's based on the valve size. It's simple stuff, period. You can test it with liquids. You can test it with gases. And the key thing is here that the criteria is visual detectable leakage for a liquid. So do I see water coming out? Then it's a leakage. And if I test with a gas, then essentially it's also visual leakage. Because either I use leak detector spray, which means that I get bubbles, and bubbles I can see, so I can see leakage. Or I submerge it in water and then I see bubbles again. So again, it's visual. Onwards. So these are criteria. Again, 100% visual. For P11, which is essentially external leak test, so it's a repetition of our strength test, but I don't need to do it at the same pressure level. So the standard actually tells you that you can combine both tests. So you can do one test and they represent P10 and P11. And again, the criteria is essentially the same. The only difference is that they demand that there is pressure on the entire valve. So in API 598, they would call it the, I think it's backseat pressure test, which means that pressure is everywhere. So you mean you check the entire valve for leakage. But again, criteria is pretty much the same, right? It's visual leakage, period. And keep that in mind, because visual leakage is something very hard to automate. So just to carry on, so we have C testing. Now this is different, because here we have acceptable leak rates, which means that some valves are allowed to leak, which means that we want to be able to quantify leakages. So this is what you do with bubble counters, flow meters, I think instruments that everyone who has done a test will probably know. And if I tie that together, we have a test process that we have to go through. The test process basically consists of, I need to do some setting up, because I mean, my valve doesn't seal by itself, so I either put it in a test bench or I put blind flanges on there. I need to do all my preparations to make sure that pressure can be contained inside that valve. That's what I call setting up. Again, we're just talking about benchmark process, so you understand my train of logic going on. Then if we're testing hydrostatically, we fill it with water. We can do test P10 and 11, which is a body test, shell test for the Americans. Then probably we have to close the valve. So this is operating the valve stem. We probably have to do 2 seat tests, so 2 different directions. We say one side is A, the other is B, so we have direction pressure A towards B and B towards A, which means pressure on one side, and the second side is the side where we measure leakage. Once we've done that, we open the valve again, we drain it of water, and essentially it becomes handling again, because we need to do something to take it out of the process. So usually setting up is clamping the valve. It's things like setting up the process, filling, it's things that don't directly contribute to the test result, but we have to do it to be able to perform the test. Then main limiting factors, especially when you talk about speed, because I discredited speed. I said I cannot be faster per se, because in fact I have limiting factors. I have a particular test time that I need to follow. It's the minimum requirement, which means that I have to do it in a particular way, and there's no way I can stretch that. So clearly, I cannot touch this. This is what I have to do. Then opening and closing, I mean, it really depends on the valve that you produce and the information that you want to gather. I mean, I could open it by hand and register no information, just to see if I operate it, does it work? I could do it automatically. I could measure torque to see what is the slipstick on my ball valve. Is there a point of resistance? I can even relate that back to, is it relevant to the process? So can I predict faults coming from my manufacturing process based on the data that I gather? But you don't necessarily have to, basically. And then finally we have handling again. So it's draining, drying, preservation, things you need to do to make sure that the valve is ready to be put on a pallet and maybe shipped to a customer directly. So this is my benchmark process. This is what I'd like to use to talk about the main subjects, the main reasons for automation. And again, I feel this is not what we're pursuing today. This is great high-level philosophy. This is a nice dream to have, but it's not tangible. It's not something you want to achieve within the next few years. I do not believe that these are the arguments you want to use. The arguments that you do want to pursue, because they will bring you some sort of benefit in fairly short time span, are to digitalize test results, to increase productivity, to have a sustainable workforce, and to have a more competitive edge. And just to emphasize, what I'm presenting here today is not a future vision, something that we're pursuing to do. This is based on projects that we've done over the past 2 years. So everything here is an example of a test bench that we built. And all of them are a combination of these arguments and a reason to invest more in an automatic test bench. So let's go through these, and I'll keep an eye on the time because I don't want to deny you your coffee break. So start with the first one, digitalization of test results. So to paint a picture, let's say I'm an operator. I'm a guy working at the test bench, and maybe I have a very old test bench and it has, clamping station, and I can increase pressure by hand, and there's a pressure gauge and it shows the needle, and what I have to do, I have to take my paper procedure, and it says fill the valve with water. So I fill the valve with water, and I do that, and it says pressurize it to the pressure level on your work order. So then I look up my work order, second piece of paper, and I look it up. This is the minimum pressure level, so I go to that pressure, and then I have to keep it under pressure for, well, maybe 1 minute. But it also says, well, they don't trust the process, so you have to get the inspector. Oh, shoot, I have to go to the coffee machine, get the inspector. Inspector, I put pressure on the valve. And what I do, I look at the pressure gauge, and I sort of think, okay, well, now I'm at the right pressure level. The pressure gauge might just be a bit too coarse. So can I really see how much pressure there is in there, so I can make a best guesstimate to persuade the inspector? I take a picture of the pressure gauge saying, this is the time, this is a picture of my watch, this is a picture of the pressure gauge, this is starting pressure, and let's count down 1 minute. And after a minute, then I take a picture again, and I tell the inspector, the pressure loss was near to none. And the inspector says, well, I'm not sure if I trust your pressure gauge, so I want to connect my own pressure gauge to the system as well, just to be sure. And then everything works out. We have a test result, and I write it down on paper, and now I have to enter it into our system, because somewhere in the system I want to generate some sort of test result on the ITP, which means that I bring my stack of papers, I go to the computer, and I type it in. And I had a good day. I didn't go out yesterday, so I did a great job, and I made no mistakes. So this is the basics, right? So digitalizing is just entering data into a system. Now, the thing with this is this good enough? Is this what we want in the future? I mean, sure. I mean, I can add a digital pressure transducer, right? So now I don't have the pressure gauge. Now I can send the data straight into a system. So it's digitalization of test results, and it brings me a bit further, and it helps me a little bit because it saves some time for the operator. It builds a bit of confidence that the test result is okay. But is it really enough? My favorite anecdote is that at some point in time, we reached out to a third-party inspection agency. So it's like Lloyd's. And we asked them, do you think we could certify the process of pressure testing of a test bench to a point where we can say, okay, this test bench does this always. So if you put something in the test bench and it comes out, you can say it's certified to some degree that the test bench does the same thing always, so the value is bigger. And we had a very big discussion on this because, they had an IT guy and he was talking about blockchain, and things got very complicated talking about data. And then one of the inspectors started laughing because, we tried to give some examples what a test bench does. And he was saying, in my previous job, I worked in a factory and we made these small flow meters for what you have in your house, basically. So it's very inexpensive metal body flow meters. and you do a strength test on them. So you fill them with water, put pressure in there, and that's it. It's all low pressure. It's cheap components. You want to be efficient. And he was saying that we were a production company, right? So we had to produce hundreds and hundreds every single day. And everything went great, but there was a moment in time where we got a complaint from every single customer. And the complaint was the build length of the flow meter is actually shorter than what you specified. So in all our preparations in these houses, they don't fit because they're smaller. What's happening? And they checked their quality record, and they did a dimensional check. So they measured every single flow meter for length and checked if it was okay. And everything passed the dimensional check. So what went wrong? Very long time later, they found out is that they had a test bench. And it was a hydraulic test bench, and it was a very unintelligent machine. So it relied on an operator. And the guy, what he did is he put so much force on the object that it actually, it shrunk. It got smaller because of what the operator did. And the reason they didn't find it is that they did the dimensional check before testing. So everything's okay. I put it in the test bench. It gets smaller. I don't check it again. And now I have a quality issue. So it's not necessarily about the test result that we're trying to achieve. It's about what do we do? What are the steps we go through that we can build the confidence that this is okay, that this is good enough. Because in a perfect world, we want to eliminate that inspector, and we want to have a process that we can execute, and the result of that process is good enough that we can accept it as this is valid, this is good enough. Because that brings you efficiency. It takes out cost. This is a form of automation. So fast forward, if we look in the industry, what are the main initiatives to achieve things like this? There's very little ones that actually come off the ground, but the biggest one, which is getting traction nowadays, and you don't see it in the news, but it is getting traction, is the Material Digital Passport. And the Material Digital Passport is ultimately an initiative which is carried by IOGP. So it's a group of energy companies who join together in an effort to standardize specifications of valves under JIP 33, and they also have a specification on how the Material Digital Passport system should work. So MVP is essentially an electronic passport, which means that every single step in the life cycle of a product, we register all of that information digitally. And anything that changes throughout the life cycle of that product, we register in an online platform, which is independent, and it relies on information coming from suppliers, repair companies, and basically the entire value chain. So the concept sounds great. And the idea is that every single valve, every single component which is relevant will get a unique identifier, which means that it's traceable in a cloud. So online the data is there. If you have a component, if I'm in a refinery, if I scan the tag number, it brings me to an online environment and all the data is there. Everything we've ever done to the valve, from the moment we started to design it until the moment that I'm standing in front of it, everything should be there. And the idea is that it becomes tamper-proof because you store data in a single place. It's much easier to find everything. And the idea is that if you get a process in place, you can make the process tamper-proof, which means that the quality of the information is much better. So I don't rely on that old picture of my operator that he took for the inspector, and then the second picture, and then the conclusion that something happened and the signature that something was okay. So Material Digital Passport is essentially it's IGP's effort to engage in a digital transformation. And digital transformation is a very nice fancy term, but what does it mean? So the digital element is that IGP says we want to digitalize information. So it's vendor data, it's information from EPCs, and data from our own refineries and plants, so we can have everything in one single location, which makes it searchable. So this is the digital effort, essentially. And then the transformation bit is that you can have a process in place, so I can digitalize everything. I can take all of my data from a valve and just enter it with a keyboard, put it in the system. I could have a clever system to scan it and put it in the system online. But the idea is that the transformation bit is actually to optimize the processes that we use. And this is why it brings it so close to the initiative of JIP 33, which is essentially a standardized specification for a particular kind of valve. So if everyone buys the same kind of valve, it means that on an industry scale, at some point, we can have one single process to purchase and to manufacture and then register all of the data from that particular valve. Which ultimately, the dream is that there is no separate system for different end users. So it's not like you work for Shell and you have to use their system, and then you work for Aramco and you have to use their system. No, the idea is to have one uniform platform, but it's decentralized. So they could have their own server, but the communication and the way you present data should be the same. And ultimately, it should bring quality improvement and optimization. So it should be a big win for everyone. That's how it's presented to all of us. So the purpose, if you look at what it means for us in the valve industry, essentially what we're trying to do is we want to take product and material properties, certificate, testing information, and life cycle information. So anything we can gather which is relevant for what we call quality of the valve, we want to digitalize. Which means that all of that data, if you generate it, which probably you should because you get an inspection and test plan, you have to digitalize it at some point. That data needs to go into a different system, and from there we consider that it's true. And the reason they want this is traceability, they want compliance, because the idea is that the spec, the purchase spec, is JIP 33. So this is what the valve needs to comply to, and if it's always the same, it means that the steps are always the same, which means that I can verify if all the steps have been done properly. So for the end user, it enhances compliance. And then finally, a good reason for them to engage in this is that there's much more focus for end users that they have to report on their sustainability. And the idea is that especially energy companies, they want to offset their carbon emissions. So reaching net zero is not about emitting zero carbon emissions, it's about compensating the emissions that I make. So I try to reduce carbon emissions and then I offset it, basically. But to offset it, I have to report my carbon emissions, which means that if you look at the scope 1, 2, 3, especially the scope 3 element, if I purchase materials, at some point I need to report the effect of carbon emissions coming from my scope 3 activities. Which means that if you digitalize it, and you put the responsibility with your vendors, all of you in the room, I imagine, it means that you get a much easier position because you get the data provided and the only thing you need to do is to report it. And don't underestimate it, because this is very important for end users. This is something that they will have to do, and they have to transition into doing that. So this could very well be the minimum that you need to do to provide valves to end users. But this sounds great, right? This is a great story, and I'll admit I copy a lot of these things from IOGB presentations because it's very general stuff, and it sounds great and fantastic, and it's the big dream that we're all trying to live. But what is the real reason why they're doing it today? So you didn't get it from me, but a guy from Petronas who is actually buying JIP 33 valves, and he is using the Material Digital Passport, so he has a platform for it, and he is doing it, and he's saying, this is the future for Petronas. Everything will go through this system. The main reason for him is actually this sheet coming from an IOGP webinar. And what it says is that the main issue that end users have is counterfeiting, which means fraud. Deliberately fraudulent data, which means that I produce something as a manufacturer, I know it's not okay, but I tamper with the evidence to make sure that it seems okay. And this is apparently a very big problem, because from statistics, every international oil company has at least 10 cases of deliberate fraud from materials that they buy. So every single energy company, every single company buying valves get fraud cases anywhere in the world. And the troubling thing is that these are the cases that they discover. So this is what they found. But it means that the ones that they didn't find, because the process doesn't allow it or the fraud is too good, they have to presume that about 95% of the cases are undetected. So there's actually quite a bit of fraud going on when it comes to supplying materials. And it goes to a point that when you speak to, for instance, Pertamina in Indonesia, who are very much a growing end user, their main issue with material supply is not getting new components. It's the fact that when they have to do repair to some sort of valve and they have to get material, they keep the material in stock, but they only find out that it's not actually the material which was specified when they try to machine it. And it goes to a point where when they try to reproduce seals based on the OEM's drawings and they machine it, then the material behaves completely different. And then they find, when they do additional testing, that it's a completely different material, which means they don't have it on stock, which means that they have downtime, and now they have an issue again. So the cost of these things are actually huge. And it seems, because I mentioned Petronas, which is essentially Malaysia, so it's in the east, it's Pertamina, it's Asia as well, so we have the feeling that it's, Asians, this is problems that happen in Asia. But then if you look at the source location, you can actually see that we're not saints. It happens in Europe as well. And it happens in America, and it happens in different places. But admittedly, yes, in Asia it happens more. And probably we can come up with the reasons for it. But still, it happens here as well. So if you want to eliminate it, you have to take actions. And that's why MVP is such a big subject for the end users. Now again, if I steal one of the sheets to show the relevance of NDP, what you can see is that this is the entire simplified process. And the idea is essentially that the end user, so the owner, has a project specification, which is hopefully based on JIP 33, which means that it's standardized, which means that they place a purchase order to their EPC. And the moment that they initiate in the project, essentially they start by creating that MVP. So this is the birth of the identifier for every single component, which is going to be used in your facility. And if you think about that, because I can talk about the entire rest of the process and they're just steps to initiate interaction between all the parties, because the EPC will buy valves from you, you will buy components from different suppliers, and everyone involved in the value chain ultimately needs to provide information, which then is verified by third parties, and all the different layers throughout the structure, which makes it a wholesome NDP. But the reality is that if we look at what NDP actually is and what the structure is, I can sort of say that it's my ITP, right? It's my inspection and test plan. Because in JIP 33, which is essentially a purchase specification, and if you think about it, every valve standard is a purchase specification. It says this is what you need to do to provide a valve. This is the evidence that you need to provide. NDP is the same, but the difference is that every component has an identifier. So it has a unique code to differentiate it from all the different other components. So NDP potentially has the ability to replace an ITP in a standardized format, which is beneficial because when you get your purchase order, it means that you already know what to do. And from the system, you will get the request basically from your ITP. This is what you need to provide in information. And the benefit of digitalization is that you tie every single thing together, which means that I don't need to enter it by hand, which would be a shame, a waste of time, but I try to automate it. This is the essence. And the interesting thing about this, and this is the question I always ask to end users when they talk about NDP and why are you doing this and why do you feel this is better? I always tell them, well, I always say, if I get input and the input is shit, it's not relevant, it's not good, it's still fraudulent, it's wrong, and I put it into the system, now I have a certified piece of shit, essentially. because the value of information is none. And the answer they give, and this is relevant in your reason to digitalize, is not necessarily about the information that you get, but it's about timing. Because when this operator is standing at that manual test bench and he is doing all the steps, he's taking his pictures and he's writing everything, there is always a delay between when something happens and when it goes into the system and when it finally reaches MVP. But if it's an automated process, so I am pressure testing my valve, I can timestamp it and I send it straight into the system. So if I know the machine provides information and it happened then and the information is provided directly, then I didn't have an opportunity to tamper with it. And that's the philosophy, and this is the underlying importance of MDP for the industry, that it's not just about providing information, it's about how you provide it. Because if you're just going to enter it by hand, it will not be enough. So let's move forward, because now we have to talk about test benches, and I have to keep an eye on the time, otherwise Virginia might be angry with me, I hope not. So this was our benchmark process. So our EN12266 valve, how are we going to test it? So the steps that we want to look at, the steps that are relevant for the MDP, they're basically our pressure test, right? So it's strength, leak tightness, and C testing. That's the minimum information that I want to provide. And depending on the kind of valve, I might need to provide some information on opening and closing of the valve as well. Especially if you're building actuators onto there, you might need to justify that. So this is all information that I want to register. I want to capture during my test. And then if I look at the architecture that we use in our test benches, which is essentially a software architecture, we layer it in 3 different levels of control system, essentially. So the most basic layer is instrumentation. So in our instrumentation layer, we have the device itself that does a measurement. So it's a pressure transmitter, it's a torque cell. It's something which is capable of measuring our process parameter, which we need as evidence for our process. Then the next layer is actually our control layer. So what does the test bench do? Now again, I'm talking about automatic test bench. And if you think about, for instance, a strength test, then a strength test essentially consists of, I fill the valve with water if it's hydrostatic. Then I want to be sure that it's full of water because it could alter my test result. If I have air, it could make sure that I do not see pressure decay, for instance. I pressurize it to a particular pressure level. I want to know how long I stabilize my pressure before I start test time. Then I have test time, and afterwards I want to release it, but it's not relevant for the result. And that's what happens in our PLC layer. So it's a PLC that controls the actions of the machine to make sure that you go through the process. And then finally, we have the way you operate it. And we deliberately use a separate human-machine interface, which is essentially the touch screen that you use to operate it, because the PLC will not determine if it's a passed or failed result. It actually happens in the HMI. The parameters come from the HMI, it goes into the PLC, PLC executes it based on instrumentation in the machine, and then the interpretation of the result and the encryption towards the system actually happens in the HMI, because that's not what PLCs are made for. So if you talk about MDP, it goes hand in hand with blockchain technology. Your PLC will not create a blockchain encrypted test result and send it to the MDP. There has to be a layer in between. So the trending things that we see nowadays is that instead of just using a pressure transmitter, you can use digital pressure transmitters. And the difference is that when I have to justify which pressure transmitter I'm using, I could say, inspector, let's go to the back of the machine, let's have a look at that serial number, you write it down, I assure you it's this one. On the certificate, I will show you this is the serial number. This is something you can very easily automate, because a digital sensor has its own identifier, which means that if you plug it into the system, it will report back, this is my serial number, this is my range, this is all the data you might need to know, and I can assure you that I'm the right component, which means that it makes it tamper-proof. So for the next layer, if I want to justify the process steps, as long as I can get in my PLC fixed process steps that I need to go through, if I can report the process steps that I went through with the measurements and the parameters that I used, I can create that extra layer of integrity, which means that I can say the result that I'm presenting is based on measurement, which is undisputable, but it's also the steps that we pre-certified. So then maybe it's not so necessary to have the inspector there because the machine does it automatically for you and it reports undisputed evidence. And then finally, that result, obviously, it has to go to the MVP, which means that I have to tie it into a system, which, consider it a cloud system, database, whatever it is, and it needs to have a communication protocol, API for the people who are into IT, which means that I have to encrypt it and I have to send it to a system somewhere in the internet. Again, it's something that my PLC cannot really do. So I need to have that extra layer in between. And obviously, you could still store all the information locally, but the idea here is that you prepare to integrate into MDP, because perhaps one day, Oscar mentioned to me yesterday, he hopes that he's retired before it happens, but it could very well happen tomorrow, that you get a customer saying, let's do a pilot, let's tie into MDP, and what do you need? So in that MVP, what happens is that you get a purchase order in your own system, which is over here on the right. The moment that your purchase order comes in, basically, you get your tag numbers, your identifiers from the MVP, which is essentially turning into your ITP. So this is going to be leading for the rest of the process. And probably you have an ERP system where you enter that data, because you're a commercial organization, so there has to be some sort of work order. Now then, two things could happen. Either it's a standard product for you, so it's a matter of press the button, and I know this sounds fantastic and might not be the case, but it's what we dream of. And then basically you get your manufacturing execution system knows this is what we're going to produce. Purchasing has to get the materials. We can schedule the work, allocate machinery locations, and you get your project scheduled, basically. And the alternative is that you still have to do design. So for the test bench, the design phase is actually interesting because some of those parameters, some of the features in your valve might be relevant for how you perform the test. It's not test time, right? Could be, but not necessarily. What it could be is that the dimension is so different that if you have a CNC test bench that you have to compensate for that. So you need to have that information in the system. And the idea is that when you design a valve, you create your design, you prepare it for the manufacturing execution system, but you also put it into the test bench, because once you've designed it, you can build it again, basically. So there's a line of communication there, which has nothing to do with the MDP, but it is critical if you're really talking about automation. Then the moment that the valve comes to the test bench, the picture is that your operator of the test bench scans his work order with a barcode, which is related to the MDP. So it means that once he selects that work order, it is the model of the valve with the parameters from the system, so the system is capable of testing it, but the criteria that you need to meet might just come from the MDP here, and not from your own system. Could still come from your own system because maybe you're doing additional testing. Maybe you're not doing a 1-minute test, but preventatively you're doing a 2-minute test. Could be, but it could also come from MDP. Then finally, you run the entire test, the entire cycle, and then you report back to the system. So essentially, your quality certificate, everything you've done as part of that benchmark process, you would send back directly into the MDP, but you could also store it in your own system. But the relevance of the result will ultimately shift to being, it has to be in the MDP. It's not relevant that it's in your own system. It's great for your own quality records. If you get a complaint, you can look back in your own records as well, instead of just looking in the MDP. But the emphasis will be that the data you collect in your own system will help you to tell you something about your own production, and not per se on the quality. because quality is defined in MDP. It's what you have to deliver. And the emphasis here is that if you look at a test bench, so the thing that we're doing on a daily basis, is that this element here, so what I boxed, this is something you can certify. This is the reason why we asked that third party, is there a way that we can certify the process of a test bench? Because if you're looking to save cost, if you're looking to be more efficient, what you're trying to do is to eliminate any losses along the way. And it's some big things like, do I need an inspector to be there? Well, if he's not there, it saves money, it saves logistics, because generally when the inspector is there, it's quite an annoying time, except if he's a nice guy and if he pays for dinner, but generally we have to pay for dinner, right? So the better I can certify this process and create that layer of relevance, the less I have to do along the way, which means that ultimately I can save money. And this is what test benches will do in the future. And this is near future. This is what we're preparing to do in the next few years. And obviously the pilot phase will be difficult, but ultimately it's something that needs to happen and we'd rather do it now. So our strategy is quite easily, we want to digitalize instrumentation, step one. So we want to have unique identifiers on the measuring equipment. And we already do it for our online testing. So product group number 4 that I introduced to you is online testing of pressure relief valves. And in that system, we only use digital instrumentation, which means that when I choose a particular instrument and I plug it into the system, it recognizes this is the range, and either it's the correct range or it's not, and then it will tell you we cannot proceed because this is not okay. And it will tell you this is the serial number, this is the calibration data, which means that when we run the test, we know this is exactly how it was performed. And we know that the test result from that particular bit of instrumentation is correct. And then the next thing is that if you go through the process steps, we are essentially steering towards a process where you cannot deviate from the right steps to follow. So you have to do everything in the right order, which means that you cannot tamper with the result. And for that online testing, for instance, it means that if you go through the steps, we actually record the steps that the operator goes through. So you get a certificate, but you also get a video of what did someone do when he was doing the test. Because it's evidence to show it's reasonable that he did it in an okay manner. And then ultimately, when you get that validated result, so you get that package of information, which is exactly what you need to report to, you would need to send it into that MDP, which is essentially, again, it's popular terms, but probably a blockchain encryption to make sure that it's tamper-proof and send it into that cloud where it's accessible to everyone. So this is the shift in test benches going forward. Now I realize, this sounds like future talks, could happen in 10 years, 20 years. I considered myself a young guy, but in 20 years, I'll be thinking about retirement. So how relevant is this? And if I have to explain to you how relevant is it, I would say argument number 1 is that end users are saying that this is going to save them 10 to 20% in costs for new projects. And if you realize how big their projects are, the cost saving is huge. So for them, there's a big drive to do this. And even their lead time will go down by 25 to 40%, which is a huge saving for them. But it turns into our problem, because they save the money, but we don't, because we have to put in the effort, which means that we want to do it in advance. We want to think about it. We want to control the system, that it works for us. Not that the end user says you have to do it like this tomorrow, because then we have a problem and then we're probably more expensive. Another interesting thing is that if you do things like this, inevitably it will be more efficient. So the investment is quite high because you have to change your processes, you have to take into account everything you need to do to make this happen. But actually, if you look at what we're trying to achieve, we're not shifting from industry 3.0 to 4.0. If we're doing this, we're getting ahead of industry 4.0. Because Industry 4.0 just means I want to capture big data so I can have an opinion about data. And Industry 5.0 is actually about how do I use that data to create more integrity. So looking into the future, Industry 4.0 is easy to achieve because I just measure something. I add a pressure transmitter, I record all of that data, and I can say I did Industry 4.0, period. Easy, easy win. Good for me. Maybe some government subsidies, love that, great. But the real story is that Industry 5.0 is happening today. So taking that data, going to that extra step in your factory. And that brings me to the conclusion, just adding a computer to a test bench doesn't prepare you for the future. There is much more to it, there's much more layering that you need to take into account, and ultimately it all ties down to that first argument. There is a commercial reason for end users to force you to do this, because they will save money. Even if you charge them more for that particular valve, they will simply tell you, you have to do it, otherwise you cannot buy it from us. So it's a good driver to do it. Now we have some room for questions. Is there anyone in the audience who wants to ask a question, maybe share some thoughts, some experiences, anything? I mean, I say questions, but discussion is fine as well. Impressions then. Did you hear anything new from what I was telling?
Frankly speaking, the digitalization is something that in the last year everybody discussed, but at least from our valve manufacturer perspective, normally everybody think about, you know, the original MIL certificate of the steel maker and so on and so on. And honestly speaking, just today I realized that probably IOGP will go also on this direction with the test benches that normally nobody think.
Yeah.
So it's
so, you know, I know what information you get from the market, because I know you've heard about Shell Falcon, which is, if you start Googling for NDP, ultimately, even on the IOGP website, you find some documentation from Shell about their pilot project for Falcon. And Falcon is essentially their effort to create this MVP system. And it's quite old, because we were involved in that, and it's been 3-4 years since we've had the latest public report saying what the effect was of Falcon. And it's a beautiful report, because it says it was a big success, but afterwards there's complete radio silence. There's nothing more. If you talk to Shell, you get no information on Falcon anymore. And this is, on one hand, it's strange, right? They invested, so why not continue? But it also has to do with the philosophy that it shouldn't come from one single end user. And that's why it's so interesting to keep in touch with the other end users who are considering to do this. And this is why I bring up the guy from Petronas, because they said this is so interesting, we're going to invest time and resources into this. We're going to start buying valves based on the project. It's based on Falcon. But the trick is that Shell doesn't want the Falcon system to be the system, because if anything goes wrong or if it takes a turn for the worst, then it's the problem that Shell created with their system. So deliberately they're breaking it up and saying to everyone, you need to have your own opinion, so we can have a decentralized system, so we can do whatever we want. And probably when the system is in place, Shell will say, well, it's great NDP, but we have NDP plus Falcon, because this is exactly how they write their specifications. They take an international standard, an API standard, and they have an opinion on what it says, and they write their own standard, which is the Shell DEPS, and they ask for supplemental information in that, supplemental steps you have to go through. And this is how it's going to form. So there will be a baseline layer, which is defined by a group of end users, and there will be always be end users which take it one step further, because they feel that it brings quality.
In the previous slide, I have seen that you mentioned Industries 5.0, and I think that, okay, everybody knows 4.0, but honestly speaking, I don't have clear idea which is the main difference. So, okay, 4.0 means connect completely the equipment to your company lines and company systems. But the main difference with the 5.0 so will be basically the digitalization
So
in a more deeply system.
it's, this is interesting, and definitely Google this when you have a moment, because there is Industry 5.0 and there is 6.0, and it's essentially a vision on what it means. And the idea is that we're coming from essentially just industrialization, which means that we're being more productive, but we don't necessarily gather data, to a point where we reach 4.0, where we want to capture big data, but we don't necessarily do anything with it. We didn't specify what the idea is behind it. Industry 5.0 and then 6.0, they actually steer you towards a concept where we're saying we're not going to customize anything anymore. So if you would ask me what is an Industry 6.0 test bench, I would tell you, you can come up with your wish list and tell me this is exactly what I want, build me something entirely custom, and I will tell you no. The only thing I will do is to personalize a standard test bench for you, because it's more efficient. So the concepts, they're very broad and vague, but they actually make a lot of sense. And they're all things that you could do already. And if you think about it, this entire endeavor starts with this JIP 33, which is a standardization initiative with the intent to have the same valves available to everyone, so we don't need to design them every single time. So you could buy the same valve from everyone, basically. Again, it's perspective of end user, which is a great cost saving. But the principle really ties into much more than Industry 4.0. And the future is not only tomorrow, the future is way ahead. Even after I retire, the future is still an evolving thing. Any other questions? Then I will... We still have a bit of time to go until lunch. So let's carry on talking about automation for valve testing. But we'll take a few different directions as well, because the MDP is obviously, it's quite a heavy subject, and it's quite, it's a big one, but it's not everything. You know, it speaks about digitalization, but there's much more aspects which are interesting to consider when you speak about automation. So we talked about the first one here, so digitalization of test results. And now we're going to talk about increasing productivity. And again, everything I'm showing you here is based on projects that we did over the past 2 years. So it's things that we actually built. So step one, just to remind you, this is our benchmark process. So still we have our EN 12266 valve, and the only thing we're pursuing for all of these test benches, just to simplify, is essentially body testing, seat testing, and everything we might need to do to that valve. So when we talk about increasing productivity, one of the first things that we can consider is that if we take the steps for setting up and handling, which is normally the task of an operator, it's someone who has to prepare the valve for testing. So he has to put it inside the test bench, he needs to put blind flanges on there, maybe he needs to operate the test bench by hand to go through particular steps. And in the end, he has to undo everything he did to the valve. So they're all steps which take time of a human being, but they are necessary things to do. So you have to go through them. And they are essentially steps that you can work on. They're things that you can try and optimize, because ultimately if it saves time, then it will help your productivity, because the shorter the process takes, the more you can produce, which means you're more productive. Simple stuff. So when you look specifically at setting up and handling, what you'll see is that about 99%, if not more, of all test benches worldwide, they're simply loaded and unloaded by hand, which means that it requires someone to be at the test bench to keep the test bench in operation. Whether you automate it or not, there is usually someone there who has to put the valves in. maybe has to open and close them as well. So this is a limiting factor, period. So the test bench can be super fast, but if we don't load the test bench quick enough and we don't take the valves out quick enough, then still it's going to be the bottleneck when we look at increasing productivity. So the obvious thing, and I'll go big straight away, is robotics. So why not replace a human being for a robot? It makes sense, right? I mean, this is what has been happening in mass production for years. And there's a tendency that we feel we're replacing human beings, and you know, we don't like that because we want people to have jobs. It's maybe a little bit unethical. Then in the valve industry, we tend to say, well, you know, our operators, they really have to do something very specific. So it has to be done by hand because there's so much variation, or you need to compensate for it because you need experience knowing what you're doing. But the arguments are not per se very relevant. I'm not saying that it's not true, these arguments, but it's not so bad as what you think. So the picture you see here is about a 600 kilogram robot, which means that when we put the gripper on there, so there's a gripper here, basically it leaves you with about a 500 kilo valve that it can lift up, and it can place it in any different position you might want to have, which means that it can replace an operator working with a crane, essentially. So those steps is what we set out to do. You can even see that it's based on a track here, so it can actually drive back and forth. And the cost of this robot might seem very excessive, but it's not. Because for this customer, it's basically the wages of 2 people for 1 year. That's the investment cost of the robot. Obviously, still you need to have the gripper manufactured, you need to do some programming. But let's go a little bit bigger and say this robot costs about the same thing as employing 3 people for 1 year. Now, 3 people working probably 8-hour shifts, right? This is the norm. So their productive time during the day is about 8 hours. So I have 3 shifts, essentially. The robot can work 3 shifts as well. He doesn't get a holiday, so he keeps on working if you want to. So it's not a very bad business case, right? Because after 1 year, then my return on investment is already done. So it's not super expensive, but I do have to consider that I have to do a lot more automation, because I have to match the different steps in my process. I can't just say, well, I have a test bench, I will put a robot there, right? So the example I gave before our coffee break, the operator, which is working with the pressure gauge and, you know, taking pictures of the pressure gauge, I really have to consider that the test bench has to work automatically as well for it to make sense. It wouldn't make sense to have a robot loaded into a test bench and then have an operator turn the knobs again. So it's always about doing more. And the trick is that if I do more, I always get the impression that I make processes more complicated. Because could you operate a robot? Could you ask of your people in your factory to operate robots? And the answer is basically no, because it takes training. You need to understand what you're doing, which means that it brings complexity, which means that you need a higher level of education to be able to maintain this and be productive. So you have to consider that, and you have to try and compensate for that, that it still works for your concept. And I want to merge it into production, so everything surrounding it is more productive. Because I can't just place something somewhere, expect the bottleneck to disappear. No, I need to reevaluate all of my different steps. So now is the cool part, because it's a video. This is the actual test bench in operation. And the background for this project is that it's a customer in Norway, and one of their products is these, basically they're multi-direction valves. And you might say, well, this is a standardized product, but it's not. Because if you look at the variation that they have, so either it's a combination of 4 valves mounted to that same center body. It could also be 3 valves, could be 2 valves, could even be 1 valve. And then every single valve could have up to 25 different process connections, which means that the variation that you get for an assemble-to-order product is huge. And this is the reality that they have to deal with. So their process is that they produce semi-finished products, which is the valves, the bodies, the process connections. They keep it on stock, and when they get an order, they assemble to order, which means that probably pretty much every single valve that goes into the machine is slightly different in some sort of way. And that is a challenge because you have to compensate for that. The process has to facilitate that. But it doesn't mean that it's a limitation necessarily. In fact, it's an opportunity because assembling the valve is something only an operator can do because he has to be conscious of what he's doing. He has to take the right components, he has to assemble them in a particular way, which is a step which is very hard to automate because of that variation. It's hard to reach places, lifting the right materials. So it's something that would cost a lot of money to do, to automate. And it's probably not worth it. But like I mentioned, this is a customer in Norway, and I'll start the video again to keep you a little bit more entertained. So one of the problems in Norway is space, because it's in the mountains, so there's not a lot of space to expand your factory. If you really want to do a big expansion, probably you have to move to a different location, which is a problem. The second problem is availability of people, because there's not so many places where there's a big workforce who are willing to work in a factory anymore. Because, well, Norway is doing quite well, wages are quite high, quality of life is quite good, so working in a factory is not very interesting per se. So, key thing here is that they did not have the people to be more productive, which means that with the people available that they have to look at a way, can we optimize this by taking particular activities away from these people and making sure we can just carry on working. So the emphasis for them is that all of their employees working on this line, they are assembling valves. All other steps they automated. So the semi-finished product, the valves themselves, they come out of an automated line. And it's high repetition, so that makes sense. It's easy to automate. Then they assemble, which is manual labor that they have to do by hand. And there's no way around it. They cannot add more people because they don't have the people, so they cannot be more productive. And then once the valve is assembled, the intention of this test bench is that you bring the valve to the test bench, you place it in a loading station, and you basically wait until the test bench is ready to go, because it will just keep on working. It will just pick the next valve which is on the station. And as long as the machine knows what kind of valve is in there, it can actually perform all the steps by itself. And then once it's done, puts it in an OK or a not OK position. And then every time the operator, so the guy assembling, comes back to the machine, he will just pick the valve. If there was a problem, he will get a report. This was the issue. You need to work on this. He does the work, puts it in the test bench again. And if it was OK, it can go straight out to shipping and receiving, basically. So for this customer, it's a very effective way of being more productive. And the return on investment is quite easy to make if you look at it in a very simplistic way, because the amount of people they would have to employ, especially considering the high wage in Norway, it's a no-brainer. This machine will work all year and it will replace 3 people. And the 3 people, if you have them, can do much more valuable jobs, which leads to more turnover for the company. So it's very interesting, but the downside is also that if those people don't know how to operate a robot, how do you maintain production? And this is one of the key things that you will see in automation, is if I get a very complicated system, am I able to maintain it? Can I run it? Can I do first-line maintenance? If there is an issue, how do I interact with the system to make sure I can keep running again without needing to call support all the time, flying people all over the world just to get the machine up and running? And this is one of the trends that we see, is that essentially we're system integrators. And what we do is we take third-party systems like robots, and we integrate it into our system in a way that the operator only works through the HMI. So the only thing you need to understand is, what do I do here? And this is a recipe-based structure, and that recipe tells you, you have to do this, you have to do that, and everything the machine can do automatically, it will simply do automatically. So the idea is that the robot portion here is tied to the PLC, which means that there is no direct interaction in the software of the robot. So my operator never operates the robot. Our system will tell the robot, now it's time to do this, now it's time to do that, and it will simply report back, this is, it has been done. Which means that in the robot here, there is a job list, and there's a strategy to define parameters that you need. So, for instance, if that location where I need to grip the valve is slightly in a different position, I need to have the parameters in place in a logical way that someone without experience can enter into the HMI here. These are the parameters, and the system should automatically compensate for that. So then the only thing that happens between the PLC and the robot is essentially the PLC saying you need to perform this job with these parameters, which means that it does the job, and while it's doing it, we're just monitoring every single step that it's going through, because then we have an impression of the status of where we stand, how is it going, and that leads to how do we operate the gripper, because there's particular steps in the job list where we have to use simple inputs, outputs to grab something, make sure we actually have it, have a good handshake protocol for that, so that we then can carry on with the next part of the job list. So when you talk about automation and integrating these systems, the rule of thumb is that, first of all, robots are not so expensive. I mean, I told you, many of the robots that we buy are actually less expensive than the car I drive. And it says something about my car, but it also says something about the price of robots, because they're all standardized. This is mass production. You know, robots are being built by robots, which sounds scary, but gives us pretty good pricing on that. And the capability is so huge, such an underestimated advantage that you could have in production, that as long as you integrate it in a way that people can work with the system in an easy way, you don't need more education. In fact, you need less education, because you can focus on the tasks that people actually need to do, like assembling a valve. So the emphasis here is that basically everything happens in the HMI. Everything needs to happen in that centralized system. So this morning we talked about the reason why the HMI would tie into the material digital passport, but it also is the way to operate an automated test bench. And all of the complexity is behind that and is managed by, well, let's call myself an expert and my colleagues who do things like this, just so you get a very simple functional machine. My phone can do so many complicated things. I mean, the calculating power of this device is immense. If you imagine that this has more calculating power than the first rockets that flew to the moon and were able to safely land on the surface of the moon, they have less calculating power than this device. And I use it to look on LinkedIn and read the news. So the potential to really unlock it, it has to do with vision, it has to do with practicality and tying into production systems, essentially. So there is no case which is exactly the same. And that's the reason why automation is so broad. But it's also the reason why we see it as something which is fairly scary, but it doesn't have to be. Because automation can solve a lot of problems which occur on a daily basis. Because I guarantee you that all of your companies at some point, either it's occurring now or in the near future, are having trouble finding qualified people to work in a production process, to work at something which is as important as testing, which is still interpretation of quality of a produced product. But it doesn't have to be robots, because many of you will have multi-station test benches. And multi-station test benches, it's a term that we like to use. It's the branding that we like to call. So multi-station basically means that I have a test bench, and instead of having one clamping station to perform one single test, I actually add more stations, but it's in the same test bench, so it gives me the impression that it's more productive. So one person can do more tests at the same time, basically. So again, looking at the developments then for these multi-stations, is that essentially we're coming, and this is, let's say, a decade ago, that machines were a single thread, single result. And again, this is terminology that we made up ourselves, but single thread basically means that the machine can perform one action at the same time. So if I'm doing a body test, it means that I'm doing a body test in all the stations at the same time. So I'm doing exactly the same thing in all stations. And then in the olden days, so let's say a decade back, you would have one single test result, right? So you would have everything connected. If I would have 5 stations, I would do my body test, and I get one single result, and if one of the valves would leak, all of them would fail. Well, it sounds a bit inefficient, but this is the first level of multi-station, right? So the next step is the most logical thing, is to add an individual result, which means that I add the instrumentation and the valves, that pressure is locked into every individual valve, which means that the result that comes out is the individual result of that valve. So if one test fails, I still have 4 good results, essentially. It's more productive, right? So if anything deviates from the standard way of doing, or there's a quality defect, I am still more productive. It does mean that I need to add more instrumentation, I need to add more valves, I need to think about the logic that the system uses, because it still has to be correct. And probably I need to add more things like bubble counters and stuff like that, which is fairly easy to do. It's just a small addition to cost. And that leads me to multi-thread test benches with individual results. And this will require a bit of imagination. So imagine that my test bench has a pressure pump. So it has the capability to increase pressure for a hydrostatic test. So in my single thread machines, I am pressurizing everything which is activated to a particular level, and then I have to wait, because then the test has to be completed, and then I can do the next step. So after my body test, I have to wait until it's done, and then I can do the C test on all of them. But the idea of multi-thread is that if I have 5 stations and I have 1 pump, what I could do is I could pressurize 1 station for the body test, and because we do a test based on pressure decay, I could lock the pressure in, and then the pump is available to work on the next station or on the next test. And the idea is that if you look at a single thread machine, essentially, if I take a benchmark for 2 valves, so let's say I have a test bench with 2 stations, so I have to load the valves. The green is what I have to do. So I will spend some time loading station 1, and it will take me some time to load station 2. I start the process, and while I do the body test, I have to wait. And there's nothing to do. Or I have some other jobs that I can do in the meantime, but I have to wait. It's up to the machine to do the work, as long as it's automated, obviously. And let's consider that I have to close the valve in between. So I did the body test, and the machine tells me now it's time to close the valve. So I go into the machine, I close 2 valves, I tell the machine, let's carry on again, and now I'm waiting again. So my screen is a bit too small, so we're only doing 1 C test now, but it could also be with 2 C tests, obviously. And then afterwards, again, I have to put in the action to unload. And while I wait here, basically I have resources, or pumps, components in the machine that are doing absolutely nothing. So they're not being productive. So if I then go to a multi-thread concept, then what I can say is, well, if I only load 1 station, it takes less time, about half the time, because I only have to do 1 action, I'm done, tell the machine, let's go, let's work, and I have to wait. Then I proceed to load the 2nd station. So load the 2nd station because I'm waiting anyways, so it means that I can be more productive while the machine is also productive. Then again, I have waiting time. At some point, I need to close the valve as well. Waiting time again and unload. So you can see that, you know, the greens, they don't overlap with each other. So it means that I am more productive if I have a multi-thread machine. So I am working more efficiently and the output of the machine would be bigger. And I can do that one more time. And still, with a third station, I don't have any overlap here. So still, I'm being more productive if I add a third station. And it goes as far as a fourth station as well. So now you can see that, again, the screen is a bit too small, but this is the optimum for my rough sketch, basically. And the interesting thing is that in the fourth station, I get my first overlap. So the first time that I have two jobs to do is in the fourth station. So it means that in reality, now I'm not 100% efficient anymore. I'm losing a little bit of time, but still, if I compare the machines, one person can test many more valves, almost double the output from a single machine as long as it's multi-thread. So if it's capable of using different resources at different times during the process. And what it looks like, again, we have some nice videos. This is a multi-station test bench. And the interesting thing is that essentially this is one test bench. It has one test system with pressure pumps, which is a shared resource. But I can independently test in all of the stations. And it goes to a point that I could have a fairly small valve in the first. And it's an automated process, so you can see that we have what we call a nut runner. So it's the system to open and close the valve. And it uses a load cell to register the actual torque along the entire way of closing. And what happens is when my colleagues put the valve inside the test bench, even though some of the steps are still manual things because they're easier to do by hand if you have big variation, he starts the test process and he loads a completely different valve in a second station. And in the third station, he could test a completely different valve as well. And it goes to a point that it doesn't matter if you have different pressure levels, it doesn't matter if you have different geometries, if you have different tools in these different stations. Essentially, you have one test bench which you could use to either test the same model simultaneously, just as quickly as you can, or if you get different work orders at the machine, and maybe you have a work order for 10 small valves and 20 bigger valves, you can have the two work orders running simultaneously. And the efficient thing here is that if you get expensive components like pressure pumps, especially when you're talking about gas testing, automatic gas regulators, which are accurate and fast, they're quite expensive. So they're all resources that you can use more efficiently simply by having them as a shared resource. So they are becoming more productive. It's like the robot. If I have a robot but it doesn't do anything, it's not productive. But if I have a task for the robot all the time, it's more efficient. And the return on investment is more interesting because I can be more productive. So that combination of all of these automated steps, if you match it to your production process, ultimately it will make you more productive without having to have more people. Because if I compare my single thread machine, so my two-station machine, with my multi-thread with 4 stations, I can see that it has almost double the output. But I don't need more people. And I don't even need robotics, right? So even if I want to, I can still rely on a human workforce to do the physical labor here. And even every single step in between, so in the video you saw these steps to open and close, they're automated. There is many cases where you don't want that, or maybe you have valves with an actuator. You could still automate it, but you don't have to. You could always have manual steps in the process, but the trick about automation is to find the most sensible workload for the people or resource working at the machine, because that will bring you productivity. Not just buying expensive toys and trying to make them look very cool, which is fun, but not very efficient. So now I'm contradicting myself here, because productivity and speed, this is what you get, right? Because you're faster to produce. But the thing is that the process doesn't go faster here. So speed is not very relevant, but productivity is relevant, because the output of a single person is the most important thing you're looking at when you look at a production environment. It's not about how fast the process goes, it's about how many things can one person do, which leads to revenue for the company. Output is sales, is invoicing, which pays our bills. So you have to match it. You have to match productivity with your process, and it's not just at the machine itself. So it's not just let's draw a square around the test bench. You have to look at what happens before, what happens afterwards. If you don't have buffers in your system, in your production system, you might have a completely different solution than when you have sort of a two-bin system where the material flow always comes in. It's what you learn when you do mechanical engineering, right? It's basics. But we tend to forget these things. And if you look at the technology, actually a lot of things are possible. And they're not so complicated because they've been built for decades already. There's so many test benches in the world that can do things like this. If you look at the person working at the machine, there is particular things which are more efficient to do by hand. And there's a good reason in the video when you see that the nut runner, when we connect it, so when we connect it to the stem, we do it by hand. And it has to do with the fact that there is variation in tolerances from the different valves. So you could try to automate it and try to have parameters in place, but the machine will never feel if it's not okay. So if there's a probability that the tolerance can be off, it means that you'll have disruptions of production, which means that the machine will say, there is a problem, I need to interact with the machine and troubleshoot. So if you have things like that, so tolerances which are off, then sometimes it's easier just to make a system which makes it intuitive to just do it by hand, because that will bring a bit of speed. Because people have feelings. They will compensate for misalignments and things like that. And machines cannot do that unless you invest in vision systems, but vision systems are incredibly difficult to troubleshoot, which means that you rely on external experts to keep production running. And that brings me to the final point of this subject, that industrial robots are not so expensive. And I know expenses are relative, but I mean, you can buy a pretty big robot who can lift almost 300 kilos for 50,000 euros, which is not a lot of money. And the one that you saw on the picture, so 600 kilogram with 6 meters of track. So it could work in the entire room. It could reach every single bit of this room, and it could lift 600 kilos all the way across the room. Is only in 150,000 euros. And the programming you can learn in a day, because it's not so complicated. It's just as easy as my phone, basically. So it's not really an argument not to do it. So here's our opportunity for questions again on productivity. I have 2 more subjects for you guys, so don't worry, I'll keep you entertained. But anyone who wants to share anything, questions to ask about productivity?
There is a witness inspection. In this case, robot is not enough, because robot can work 24 hours a day.
Yeah.
Inspector 6 hours a day.
Yeah. Yeah.
So in this case, the robot can work 24 hours.
It's a good question, and inspectors are quite lazy if you think about it. But so if you look at situations like this, if they have an inspector, what they do is they try to create iterations, right? The success of production planning depends on knowing what will come. It's never an estimate. It's never a guess. You know that you have material coming through. You know that it's going to be inspected by an inspector. So it could very well be that you have a very manual test bench where you spot check for the inspector. So you're running through production. It tells you that the quality is good, and everything he wants to see, you do it separate from the production line. Because if you have volume, you never want to interrupt the production line. So that's strategy number one. Strategy number two is that if you don't really have that volume and you can afford to interrupt the production line, you can still go in two directions. So first of all, you can certify the process, which happens for many of our customers that actually do larger batches of the same valves, which means that you get a notified body to classify this part of the procedure is okay. So the output of the machine you can believe. You're just going to verify if the machine still goes through these steps. Because then it's not about the valve, then it's about validating the process. If you haven't done that, you could still say, well, you know, maybe I want to run the machine in a manual mode. So I sacrifice productivity. I'm considering to stop my line, and maybe I have an inspector for 6 hours. So let's spend 6 hours doing the testing just with the inspector. And we don't go full automatic. We just show him on the valves he wants to see. Step by step, this is it. Do you want to do your visual inspection now? Sure. Here's the interruption. Go ahead. Connect your pressure gauge, your transmitter. Because even fully automatic machines, like I have a self-driving car, but I can still drive it myself. I choose to run it automatically or I choose to run it manually. So the one thing doesn't exclude the other. So as long as you have a bit of flexibility and you thought about it in advance, you can always match it with the way that you're working. It's not a sacrifice, basically. I hope it answers your question. Anyone else? Questions? Remarks? Then we'll just carry on, because we still have a schedule that we have to keep. So the next thing, which is perhaps the most relevant subject today, workforce sustainability. And what do I mean by that? It's simply getting people to work in your factory. Because if you rely on a workforce, you have to have people who are capable of doing the work for you. It's a very simple thing. If there's no people, you cannot be productive. And the interesting trend is that even the European Union basically says, well, there is no lack of work. Our economy is in a good position. We have plenty of work, we're getting plenty of orders, so there's many things to do. But the thing we're lacking is the hands to do the work. So we lack skilled people to actually deliver the material, ultimately. So to do the machining, to do the assembly, to do testing. So it's a big concern. And you'll probably notice that, especially with a younger generation of engineers starting their professional careers, they have a completely different interest. So probably your most experienced worker who might retire in the next 10 years, you will never be able to replace him with someone who has the same working mindset, because the mindset is simply different, which means that you have to do it in a different way, because there is no one-in-one replacement. And this happens everywhere, right? So in the Netherlands, we struggle to get the right people to work on particular jobs, and we struggle to keep them. Because how do you keep people interested, especially in a repetitive job like testing? Because ultimately, working on a test bench is repetitive work. And here, automation creates an opportunity to interest people in the job that they have to do. So it creates a profession which is a little bit more than just performing manual labor. So we're steering away from factory work and we're offering more interesting career paths. And one of our customers, which to me is the most compelling case, how you could approach this, not saying that this is the way to go, is a company in Switzerland. And Switzerland has notoriously high wages. And it doesn't sound like a great place to produce at all, because the wages are high, land is quite expensive, so your building is expensive, energy is fairly expensive, so it seems like a very inefficient thing to do. So obviously at some point they had to realize, how can we stay competitive within this situation? And the first thing is, well, let's move a part of production to China, which brings its own problems, and let's move a bit of production to France, which is different problems. But still, they kept one of their factories in Switzerland, which is one of the most productive factories. And there they said, let's change our production strategy to a point where we don't have individual job positions in the factory anymore. So when material comes in, every single step of the process, whatever we do to the material, whatever we do to reach our final output, which is a fully assembled, fully certified product, one person must be able to do every single step along the way. So one education, and you can run the entire factory theoretically with one person. That's the idea. Still, you would have many people working because the workstations could still be manual processes. So how do they do it? The first thing that they did is they standardized their production system. So it's the digital system that they use. It's what they call their production client. And their production client is essentially the system that runs the entire factory. So everything that happens in the factory is effectively controlled by the production client. And what it means is that it's essentially a piece of software which runs on every single machine in the factory. And the only thing you can do as an operator in that production client is you can scan a work order. You can confirm that it's actually the work order that you scanned. So it's an opportunity to see if there's a mistake. And if something really goes wrong, you can abort the process because then there's no point to continue. So I can only do 3 things, and I cannot change any parameters. It's the only thing I need to do there. It's literally one button. First time I press it, scan the work order, barcode scanner beep. Second time I press the button, it's okay, basically. And then to facilitate the process, they try to parameterize everything. So everything that comes out of design phase has to match the production phases. So every bit of dimensions, process parameters that you might need for a machine to be able to perform work has to come from their system, which means that their criteria to complete a design is much more elaborate. So you spend more effort up front, and you should win it back later on in the process. And then to monitor performance, because still you could have someone working in the factory, but you would like to know if he's efficient. This is the principle of Industry 4.0, right? You gather data and you figure out, based on the data, am I being productive? And instead of looking at individual parameters, they said we are going to monitor machine states. So every single workstation, every single machine, whether it's a lathe, whether it's a machining station, maybe it's tube bending, welding, brazing, everything is monitored based on machine state. Which means that they get an impression of productivity rather than guessing, is the machine busy, yes or no? And I'll elaborate on that a little bit further. So if you look at the way that their system is organized, so their production client, essentially they're saying we have a purchase order which goes into our ERP system, and from the ERP system essentially we know what the production client needs to do, because every product is a combination of materials which is known in the ERP system. So what we're building is a combination of things which have been engineered and have been purchased, etc. So the production client is actually directly controlling the HMI, which means that on our test bench, you have 2 screens. One of them is our software, which tells you exactly what the machine is doing. But the way you operate it is with their production client. And if you press OK, their software layer will control the test bench itself. So to do that, obviously from the ERP system, you need to have data entered into the database. So if you have a different pressure class, you need to have that deviation inside the production client linked to a serial number. And if there's an engineered product, so maybe it's an engineer to order, then you need to have input from the engineering department. And from that database, everything is loaded into the test bench, basically. So the critical layer here is actually that their software operates our software, which sounds strange and a bit inefficient, but it's actually logical because our software is standardized, because we build 300 test benches per day, and their software is standardized to match with all the different machines in production. So it's a one-time effort to develop it, and you can repeat it in all the different test benches. So then if you look at communication, basically all communication is through an OPC UA structure. And if you're not familiar with it, it's essentially a communication protocol where every bit of data has a fixed location in sort of a framework, an architecture. And instead of sending information to someone and hoping that it's received, basically you say, I make the information available, which means that I can read that information for the entirety of the process until I take it away. But in the meantime, I look at process states to see if I can carry on to the next step. And this is a bit abstract, but basically what we do is we report the machine state in the PLC, and their production client sees it is still busy doing this, so I need to still keep presenting this data. A consequence of this is that if you don't have data, you cannot produce, period. So everything needs to be entered, and it's not up to your operator to enter that data manually. No, it's entirely up to the system, so engineering, sales, wherever the information needs to come from, that the information is complete in order to be productive. So two things stand out. First of all, the experience for the operator. If I'm at my workstation, if I'm at the test bench, I want to work with zero effort. So I scan my work order, and I expect that I only have simple tasks to do, which means that my test bench has to compensate for every single parameter which is related to that valve coming in. So what we did in their test benches is that we added features that we need to reasonably assume that things are going okay. And the first thing is that we added load cells because the valves are quite critical to overcompression, which means that we want to have control over clamping force, and we want to measure it, and we want to report it. It's an important step for their specific product.
But, sorry, it's like some, if I use a blind flange.
Well, you know, it's slightly different. So it has to do with geometry.
Because Aramco asked to test the valves, okay, at different sizes, to test with blind flange, okay, outside the test bench, because they wanted to see the enlargement of body. Okay, with this situation, I can solve this problem and I can test the valve on the test bench or not. And anyway, if you have, or if you study, because you are a partner of Aramco, okay, if you study this request from Aramco and develop a machine.
It's a good question, and it would have been my next point, right? So we're able to measure force on the body, so compression of the valve body, basically. And then to limit force and to have an effective control system, we have what we call self-energizing test tables. And it's a way to generate clamping force, which is solely based on the pressure inside the test object. So there, it's a 100% mechanical system, and it always gives a steady extra clamping force, basically. And this is one of the points where, for instance, Aramco, they say you cannot have force on the body. This is why in many of your factories you have a lot of these different radial seal plugs, inner seal plugs, with an O-ring that seals on the inside. And then if you have a difficult inspector from Aramco, he will say, yeah, but the O-ring on the inside means that we're not testing the entire valve, which means that you have to use blind flanges, basically. So it's a very annoying thing. But the trick is that if you look at these processes are, they're validated with the end users that they work for. So the moment that they design these processes, they make sure that the majority can actually go through this process, so they can accept, okay, the majority is tested in this way, and there's a little extra force on the body, but it's manageable, so it's within a tolerance that you can verify, so it's acceptable, but still, in some cases, you might want to test with blind flanges. And if I just quickly go back to the picture, actually what you see is, this is the clamping station here, and this is a separate station for blind flanges. So if it happens, you can still do it efficiently. That's the idea, and that's the functionality of productivity is to have the capability to do the things that you need to do in an efficient manner. It doesn't mean that some things you never have to do anymore. It's great if you don't have to, but sometimes it's not realistic.
Because you know, when I need to use the blind flange, I need to use also to tighten the bolt, okay?
Yeah.
And it lasts a long time to test.
It takes a lot of time, yeah.
So if you have an idea, because until it's maximum expression.
I can tell you our experience about that because I discussed for many years with Aramco about that, and this is, I think that is a proportional cylinder that basically on the calculation increase the force. So they, formally speaking, they don't recognize the system as valid. That is the system that all the benches have. So they insist that they won't have a blind flange for the load, just don't have load on the body and so on and so on. As you said, the problem is that if we speak about a rest phase, it's not a big issue. We have the O-ring, so you don't need to apply so much force because O-ring compensates. The main problem, for instance, is that when you have the ring joint. In such case, our experience, well, we don't have any official authorization from Aramco. You know, it's just something on the floor. But we experiment and we have good result with the plastic ring joints. Yeah. There is a company that produces plastic ring joint. You don't need to apply any crazy force, so you don't used to use NR pack or hydraulic closure or whatever. It's something in the middle that could help you because they said, okay, you are not testing the ring joint groove. Someone could say, yes, but with the plastic ring joints, you have not the right configuration, blah, blah, blah. But just to tell you something, in the last years, Aramco accepted to utilize a plastic ring joint that could be something in the middle for save some more time on the ring joint. Yes.
So the key thing here is that you want to have a process which is accepted by your customers, right? And if you can stretch it and have a clever technology to make your life easier, as long as your customer accepts it, and you always do it in the same way, then it's likely that they will accept. But if you do it different every single time, then probably they won't accept. So it's one of the things to keep in mind. I think we have some echo, by the way. I think you're struggling with that, looking at the technical team in the back. But I'll go back to my... better? I don't know. I'll just keep talking to fill the room. But the idea here in this production setting is that so yes, we use self-energizing test tables because it means you don't need to set parameters for clamping force. We have these automated valve supports, which means that the valve is always aligned in the center of the table. And because the length of the clamp is set to the right length, basically the machine opens the door and you can only put in the object in exactly the right position. So the only thing you do from a production line, from a conveyor belt, you pick up the object, you place it into the machine, you press OK, and then it closes up. And that just makes it a zero-effort job where you can't really do anything wrong. But you do have to keep in mind that you need to take extra steps for when something does go wrong. So, for instance, we have object detection, just to make sure that if there is an object inside the clamping station, that we can detect it. So if it should be there, we know. If it shouldn't be there, we also know. So it generates an error saying something is wrong. We even go to the point that one of the criteria is the length of the object, because there's different lengths of valves. And it's an indication that if I put the wrong valve in the clamping station, it might have a different length. So if you measure the length, then you know if the operator is doing a good job, yes or no. So it's really about trying to make every single step more ergonomical and more foolproof for the operator so he can just work efficiently. And then the second thing which is interesting.
Just to come back to the previous Regarding the automated valve support, it's just my curiosity. What is that angled part of the support where you see the 44 degrees of the metallic parts?
So deliberately, this is not the final product. It's not fully assembled because we can't show you the entire thing basically. But the idea here, the construction is that so this is the main clamping construction basically. So this is the rigid part that every clamping station has. And what we do here is we put the valve supports, we attach it to the base frame of the clamping station.
Okay, just to support the...
And the idea is that ultimately there will be a small V-block here, which you use to align in front of that self-energizing test table. And because it has a fixed distance from that table, you don't need to adjust the length because it goes with the length of the clamping station itself. And this makes sense because the products that they produce, they standardize it in such a way that we can always support the object on the outer diameter of the flange, essentially. So it's a strategy that when they produce a new product, they have to make sure it fits inside the test bench using this strategy. And one of the parameters that they have to give before they can produce is that they put outer diameter in their database. So when we know this object is coming in, we need to pre-align the valve support to this height, which means that when the door opens, I put it in position, and I can only fit the object that is supposed to fit there. So it's a self-aligning machine, essentially.
But also the plastic handle connected to the right support?
Yeah, you mean
right
this one?
column is a support, that one?
Yeah, and this is, they have some objects which are top-heavy. So they place them in, and they have a tendency to tip over. So we add this, that if it happens, then it sits on the support. But it can still move on this column, because sometimes you get a very small object, sometimes a very big one. And this is a very typical step where if you would automate this, it would be fairly expensive, and you need a lot of parameters to make this work. But if the operator puts it in and it falls over, it's easy to just slide it in place, and we're done. So this is the balance between automating and then having that the feeling of the operator working together. Yeah, it's height controlled with servo motors. So there's exactly. Exactly. So it's just tools to make things easier for an operator, which result in him being more productive. So one more thing, just to jump ahead. So if you look at standardization of machinery, there is a principle called ISA 88, which is a machine state model. And it's the intention that if you standardize the state of a machine, all of the infrastructure in your factory could rely on data based on the state of your machine. And this is a standard which has been out there for a very, very, very long time. And it's a model which basically says, how do I handle situations in my machine state? So there's different routing, which is not per se relevant for this presentation. But this is an international standard on how machines should work. And if you look at machinery in factories and how they actually work, many of them, they don't really use this state. And the opportunity here is that if every single machine in your factory follows the same protocol, it's actually a lot easier to tie into different systems. So you can optimize your Industry 4.0 effort because you can measure much better what is going on in your factory. But even if every machine works in the same way and the communication protocol is always the same, then it's not so complicated to look at things like the material digital passport, because you do it in one machine, which means you can do it in all machines. So we'd like to think that every single machine that we produce is built in accordance with machine building standards, which is the most important one for us, ISA 88. So the thing for this customer is that they are based in a very expensive country, basically. They have a very strange competitive position, but they managed to have one of the cleanest factories that I've ever seen, to a point where literally every single workstation I could operate with maybe 10 minutes of training. Which means that for them it's a lot easier to take a workforce with much lower education and present it everywhere in the factory. So you can think about things like job rotation. It's not so complicated, because if I want to have a different job for next week, I don't need to give them very particular training. It's very limited training, and still I can make the job a lot more interesting. And even if people decide to leave and you need to find replacement employees, it's much easier to train them and work in a factory in an effective way compared to having people that actually need a big skill set to go through these different production steps. So the interesting thing for us is that because they standardize processes, it also means that for the thousands of different products that they make, we manage to standardize to 2 models of test bench. And with those 2 models of test bench, they can test every single one of their products without compromise. And it goes to a point that when they have their factory in China, if they want to increase production over there, they simply copy exactly the same machine, place it there, and it ties into exactly the same production system. So every single factory of this customer runs in exactly the same way. So you can even have a person from their factory in France who can easily work in Switzerland. Questions on this? Because I still have one more subject before lunchtime, so I need to speed up a little bit.
I have one question, probably I don't know if it's the right moment or later, just to understand if you have any solution for the test with the kerosene that is typically asked for alkylation valves,
Yeah.
UOP service and so on, because we have many issues about obviously safety due to the ALTEX issue, but especially due to the operator that have some problem with the skin and the kerosene.
Yeah.
So I don't know if there are also some accepted alternative. Now some customers change a little bit. They accept some.
I have the answer for you, because we get these questions,
Okay.
and we actually put in the effort to see, okay, can we replace kerosene with something else? And the answer is yes, because if you look at kerosene, which is jet fuel essentially, jet fuel systems, like an engine of an aircraft, when they test it, they don't do it with kerosene always. They have what they call calibration fluids, which are available in the market, which means that it's non-flammable and it's not as bad for your health, and you can actually store it in your factory. So it's more practical because of the health and safety element. But it behaves the same way as kerosene, and the argument of corrosion and things like that you don't get, because it's an equivalent. But the key thing, and this is what many people don't know, is that testing with kerosene is horrible. And it's horrible because if you pressurize kerosene, you will actually entrap air bubbles into the kerosene. And this sounds a bit strange, but if I take a valve and I put kerosene in there and I pressurize it, inevitably what happens is that I get very light chemical bonds, which when I take the pressure away, will take hours, if not days, for the gas to gently come out again. So a very typical thing that happens if you do a C test with kerosene or an equivalent, so any hydrocarbon, and there has been pressure inside the liquid already, you will see bubbles and droplets forming from your droplet counter. And it has nothing to do with leakage, it has everything to do with the gas escaping from the liquid again. And anyone who will tell you we have a test bench and it works perfectly for us, they cheat the system. Because if you look at the geometry of the pipes that they put inside the test bench, they just try to make it in such a way that if gas accumulates, that it doesn't push out the liquid immediately. And there's tons of test benches that have that. They have little cheat systems hidden somewhere in the piping, in the tubing, which makes sure that you don't really see that gas coming out. But it also means that if you would take a calibrated leak, so basically an object of which you know this is leaking, and maybe it's 1 droplet per minute, I guarantee you 99% of those machines will not detect those leakages. So the perception that kerosene is a good solution for testing, the only thing it really helps to is to say, I don't want to put water in my valve because it leads to corrosion and it's going to be used for hydrocarbons, so it just leaves the state of the valve in a better condition. But when you look at accuracy for pressure testing, kerosene is horrible.
Yeah,
it's terrible.
They
It takes
very old specification. I think that the UOP is the only service affiliation that still requires something like that.
At some point, we had a test bench where we invited a customer over to justify that behavior of the gas degassing. So what we did, we put a small container, we pressurized it, and we left it there for a minute. And then we had a glass tube with like a neck in there. And what you could see is literally for days you would see little bubbles forming, and it would gently build up into that little neck. And the effect would last for more than a week. So you have to imagine that even if you do one single test with kerosene, so maybe Monday morning I did my first test with kerosene, it means that every single test that I repeat, I have to consider that there is still gas coming from that liquid, which ultimately affects my ability to measure leakages based on droplets, based on bubbles, because it pushes the liquids out, period. So it's not an accurate way of measuring. But I like the question because it brings me to my next point, and again, I have to speed up because otherwise we won't have lunch. And the final bit is about competitive edge. And for me, competitive edge is about having products which are sellable for a good, acceptable price in the market, basically. And for me, it starts with an anecdote of a customer reaching out to us saying, we have a new production line. We have a completely different strategy of manufacturing our valves, which is unprecedented. It's top secret, blah, blah, fantastic. But we have a fully automatic welding cell. And straight after welding, we need to test the valves for a body test and bidirectional seat test. But the trick is that we only have 83 seconds per valve to do the entire test cycle. But the standard says that you have to do 1 minute of body test, 1 minute of seat test A to B, and 1 minute of seat test B to A. So I have a minimum of 3 minutes of time that I have to be waiting, but I only have 83 seconds, which is just over a minute, to run the entire test, all 3 tests. And obviously, they had their welding cell, limited space, so you could think about multi-stations, but ultimately it wouldn't match in the footprint because you would need too many stations. And also, if you add more stations, you need to add more robots to facilitate all the stations. So the bigger it would get, the less efficient it would be. So the thing we did is we decided to replace water with forming gas. And we'll talk about forming gas after lunch as well, so I'll get in much more detail afterwards. But the idea here about forming gas is that we take away the limiting factors for our body and our seat tests on the foundation that gas leaks quicker than water. So we should be able to detect leakages quicker. And the reason we did this is that if you look at EN 12266, it actually allows you to deviate from test pressures as long as you provide evidence that the test process is equivalent. And one of the strategies commonly used is to use statistics for that. So basically you're saying, I have so many tests that go okay, so it's probably the quality output is good enough. But if you use the physics of the difference between liquid and gas leakages, you can actually provide evidence that it actually is equivalent with a much shorter test time, because you can compare the two. So there was some basis to do this. So it's not a cowboy project. It's actually allowed in a particular way. but we tried to steer clear from statistics and look at a physical process because it's easier to justify and have the process certified. So one of the things that we did is we took valves from production and we took all production defects that they had found over the past years on equivalent valves, and we built a small prototype setup to see if we could spot leakages and how much time we would need to see those leakages. And one of the portions there is that we looked at body leakages. And I know it's a terrible picture, but over here you can see a very small defect, which is essentially the weld being cut short just a tiny little bit. So visually you could see that it's incomplete. So you would probably say, well, this is not good enough. Maybe I want to scrap it or I want to repair it. But the reality is that if you do a pressure test on this based on water, you would never find a leak. So what we did, we took this valve and we put it into our prototype. We tested it with forming gas. And what happened, we put pressure on there, about 60 bars, I believe. And the prototype, within 2 seconds, said, there's a leak, period. So it's reject. Good. Perfect. Then we got curious and we put it into a hydrostatic test bench because it's always interesting to see, I mean, if it's a reject, how would it look with water, right? It's interesting. We're curious, we're engineers. So we put it into a hydrostatic test bench and we tested it for the specified test time and we didn't see anything. We even left it overnight, so for 24 hours to see if we could see water forming on that point of the defect, and we couldn't see anything. So then, because we were doing prototype validation, we were running hundreds of different valves just to make sure that the prototype actually works and that there is good foundation that the process works. And at some point we decided, well, let's take this valve again, because this was the first one that we did during the day, and we put it back into the prototype. But then we couldn't find a leak anymore, which was very frustrating, because it had been leaking before. We know there is a defect, so what is going on here? And the interesting thing is that it actually took us hours to figure out what was going on, because when we left it under pressure for 24 hours, still we didn't see a leak. Then we tried to clean it, because maybe there's some water in the defect causing it to be clogged. Well, we couldn't really manage. So at some point we put a heat gun onto the point of the leakage for a couple of hours, just to try and evaporate that little bit of water that could be in there. And after introducing heat for about 3 hours and putting it back into a prototype, then we could see our leak again. So we had temporarily hidden a leakage by doing a hydrostatic test in between, even though the gas test would immediately fail on this production defect. This was quite interesting, because then the definition becomes, how do I define a leak-tight valve? So we turned to theory and basically said, well, an absolutely leak-tight valve, then we have to consider that there is a defect, and if there's water in the defect, we can consider that the water is essentially in a capillary, and if the capillary is in equilibrium, there is no movement, which means that there is no potential for the droplet to move outside of the valve, which means it's absolutely leak-tight, even though there is still a microchannel towards the outside. So we did that. We calculated that based on the parameters, the materials, and we found that this would be the maximum radius. So this is the point of equilibrium. But it doesn't really tell me anything, because it's just a very small number, essentially. So then we figured, let's switch to, what if we take that dimension of the capillary and we calculate the gas leak rate? And that's an interesting thing to do, because now you could see, well, actually there is something coming out of there. So when it's absolutely leak-tight in water, it would still leak with gas. But the reality is that if you're a bit familiar with fused emission leak rates, you know that the units are a millibar liter per second, and probably you know that class AH valve is pretty close to what is the natural background of helium in the air, right? So it's already a very small number, and the magnitude of that number is 10 to the minus 6. Our number is 10 to the minus 11, which is dramatically lower. And if you would ask me, could you measure this? Yes, but not with the techniques that we use in the valve industry. Then you would have to go vacuum chamber, over-engineered, ultrafine vacuum. So you could, but even space agencies would not consider this to be a leak. So the magnitude is it's a bit overkill, basically. Because the standard, the only thing it asks of us is that it's leak tight for 1 minute, and then it's good enough. So that should be the sort of criteria that we look for. So it didn't really give us a clear answer, because hopefully we were hoping for such a clear number that we could say this is absolutely leak tight. And testing with gas, makes it much easier. So how do we approach leak tightness then? And it raised the question, can we actually predict water leakages or gas leakages based on test results that we get? And that was quite an interesting exercise, because what we did is we took our valve, so the one with the defect, and we made sure that it had no water in there, so it was actually leaking. And with a hydrogen leak detector, we did a measurement. And that measurement gave us a value of 1 times 10 to the minus 3 millibar liter per second, which is quite poor if you talk about fugitive emissions. So it's quite a big leak, basically. Based on that, we calculated the defect size, which is a much bigger number than our absolute leak tightness. And we calculated how long would it take for one droplet to form on the outside. And now everything makes sense, because we kept it under pressure for 24 hours, which was not enough, because it was actually nearly 30 hours. So the trick is obviously that if you're in a workshop environment and you leave it under pressure for such a long time, probably the water will actually evaporate before the droplet will form, right? So the probability that you would ever catch a droplet on this particular valve is near to none. It's not realistic. But if you do this exercise with different sizes of leakages, actually you see that the correlation is quite predictable between them, which means that based on the gas leak rate that you see, you can actually predict whether it would leak within a particular time span in water. So it actually is quite a predictable process. And with that in mind, we actually we built the machine for this. And the idea behind the machine is that we are just looking for pass-fail results. So this was for FAT in our workshop. In reality, it's actually built into a welding cell, so there's absolutely no human interaction whatsoever with this machine. It runs 100% automatically, and it uses hydrogen leak detectors to follow leakage paths where there's a probability of leakage. And the moment that it's not actively following a leak path, the sniffers will actually spot out different locations to see if there is leakages from improbable locations. And the most interesting thing about this is, first of all, that cycle time, we managed to achieve it, because we managed to do 1 valve every 83 seconds, which is fantastic, because we saved so much time, which is good for the competitive edge of this customer. But more interestingly, do you remember that we talked about the criteria for a body test, which is essentially visual leakage? So in any automated test bench, based on a liquid, the only thing you could look for is pressure decay, which is a notoriously bad indicator for leakages, because it's influenced by volume of gas present, it's influenced by temperature, and it's very susceptible to me having a bottle of wine the evening before, because it relies on someone watching if there is a leakage. And this concept uses hydrogen leak detectors, so it means that any leakage on the outside, actually, you can detect it automatically, because it's an electronic signal. You can even quantify it. So you can even say, based on this amount of leakage, I know what the production defect is. And the interesting thing is, actually what you see is that if a particular amount of leakage comes out of the body, it actually indicates that there is a misalignment in the welding jig of the valve. So if you get a valve above a particular criteria, it makes more sense to stop the line, make your correction, because there's no point making not okay valves. So the print also works for seed testing, by the way. So we do the same thing. In your seed test, instead of looking for bubbles, we measure concentration, basically, on the pressureless side. And because you can measure much lower concentrations, it helps you to find out quicker whether there's a leakage, yes or no, period. So the combination of all these things come up with cycle time. And the key benefits here is the body test is automatic, so the process is certifiable by notified body. So this customer actually went through the trouble to have the inspector validate the process, which means that if there is an inspection, the only thing they need to do is to revalidate the process. They don't need to look at individual valves being tested, because they just check if the machine still does the same thing. The success story here is that they can now produce 250,000 valves without any human interaction from a single line. And it's divided over 2 test stations, which makes it incredibly compact and quite efficient. And if you think about it, it ticks all the boxes for an Industry 4.0 solution, right? So our purpose of reducing cycle times, we managed by changing the test fluids to forming gas in our case, integrating robotics for the hydrogen leak detectors, because it would eliminate the need for workforce, and then automating all these individual processes. So it's things like increasing the pressure, it's opening and closing the valves in a way that it facilitates productivity from the machine itself. And then the digitalization part is actually that it's a certified process for this customer, right? So there is no need for inspection. I've seen the time, I'm nearly there, no worries. It allows remote inspection, because the inspector doesn't need to be there. He can simply watch on a camera that his tests have been performed. And if you record them, he can even do it in his spare time. And because it's digitalized, you can actually tie the test results into the material digital passport, and you can use the data to run a smart factory, because it gives you the impression whether processes are still running stable. And then finally, some insights about gas testing before we go to lunch. So if you look at our example valve, that little defect that we could hardly see on the picture, you have to realize that that valve would have passed a hydrostatic test. I could have pressurized it for 1 minute, I would not have seen anything, which means that it would have went to the field. It could have been installed, but it would actually have a carbon footprint of over 0.5 kilo per year coming from directly that leak point. So 0.5 kilo of CO2 emissions per year, which doesn't seem like much, but if you realize that end users of valves report that 25% of all leaking valves in the field are related to pinhole leaks, so similar leaks to what you've seen there, it's actually a huge effect. So testing with a gas actually matters quite a bit for the test result. And with that, I will not deny you lunch. Well, I hope you had a wonderful lunch. I sure had. Very nice. So now our afternoon program, and we have 2 different subjects on the schedule this afternoon. First is the forming gas story, and we talked about forming gas a little bit before lunch. So now let me tell you the background of how we came about. And then afterwards we'll do a very short break. So it takes about 1 hour, the presentation part, questions, and then we will switch to testing at minus 250 degrees Celsius. So forming gas to me is what I would call the forming gas story. And the forming gas story for me is basically, it's an idea that came up during an event. And if I talk you through it, in 2002, we were considering to do something with hydrogen when it comes to testing. And everyone was speaking about hydrogen, but we didn't really know what was happening in the market. So we invited Shell Global Solutions, the energy company, from The Hague over to our stand at Valve World just to have a discussion to see, could you tell us anything about the market? Is there anything we could tie into and just learn? So we just had a very informal chat with them. And one of the things that happened is that we asked them, do you have any concerns when it comes to hydrogen? And they said, we're concerned that helium is too expensive, so we need an alternative when we're looking at fugitive emission testing. And coincidentally, we had taken a hydrogen leak detector with us to the trade show, which we had in a small cupboard somewhere in the office for about 15 years. And we just took it because we were looking into a different project for that. And we mentioned, did you consider forming gas? And they said, we don't know about forming gas, but maybe. And they had to leave, like busy guys, they had to go off to their conference presentation. And the thing that happened is that a month later, they called us and they said, you have to come to The Hague. So we were summoned to come over, and they told us, well, we took the idea of forming gas and we tried to find out if we could use it for fugitive emission testing, but we could not find anything on that subject because it hadn't been done for valves before. So we didn't know if it would work. But the interest was quite big because the promise was that forming gas was a much cheaper alternative compared to helium. And the idea is that if you do production testing for fugitive emission, you want to be cost effective, and you also don't want to be reliable on a finite resource. And finite meaning that there is limited supply. So maybe one day your supplier will tell you, I cannot get the gas for you. Which means that either you have to waive testing, so you do not do the test at all, or you choose not to do the test and just wait until the helium comes back. So it's a huge liability. So because we didn't know it would work for valves, we decided that we would collaborate with the intention to see if forming gas is a viable alternative for helium, for fugitive emission production testing. And we're not going to do it because it's a commercial project for us. We're not going to do it because it's exclusive to Shell, but we will try to find out for the industry as an opportunity to bring us further for the future. So we joined forces not so long after that Valve World. And not so much later, I can see that the year is wrong here, but it was actually in 2023, we started a research project. So Shell funded us a little bit to find out, can we make forming gas work as an alternative to helium? And ultimately, in that same year, we found that it is actually a good alternative, that as long as the conditions are good and you follow the right requirements, you can actually use it and it saves you money. So the thing we did is that we wrote a paper for the American Society of Mechanical Engineers just to provide the evidence that it actually works, that it's something you can repeat yourself. So we did the work, but everyone can repeat it. It's not our property. There's no intellectual property. This is us being selfless. And taking the opportunity, we wrote it into API 6D for hydrogen valves because it was written at the time. And also we wrote specifications for Shell so they could start production testing based on forming gas. And the approach of the project was basically we wanted to find an alternative for the volume of gas being used. So that's why we focus specifically on production testing, because the presumption is that the majority of gas consumed comes from more tests being performed, which is generally during FAT. So if you're doing design validation, for instance, you might still use helium, but the amount of helium that you use for the fugitive emission test is much less. So the effect on cost is the biggest for production testing. And the thing is that we didn't just want to blindly try this, right? Not just take a valve, put helium in there, measure, put forming gas in there, and just see if it works. Because we want to be analytical and we want to understand the conditions. So we write something which is sustainable for the future because it's a quality test. We don't want to compromise on that. And that's why we said, let's look at the theory first. Let's try to understand how fugitive emission testing would work before we switch to a test setting where we validate based on calibrated leaks, which means that we know how much leakage comes out, rather than just taking a valve and see what happens. Because we want to compare. We want to understand what's happening, so we need a reference point. So that's our third step to test based on calibrated leaks. And then finally, based on that data, we wanted to test on valves, but in collaboration with valve manufacturers, because ultimately the FAT would take place in a manufacturing environment, so we want to validate that. And one of our candidates was actually Oscar here. He was kind enough to invite us, and we spent a day validating whether forming gas could work for fugitive emission production testing. And the interesting thing along the way is that we found that there is there's a lack of knowledge when it comes to leakages altogether, let alone fugitive emissions. Because when I speak about leakages, I think they're quite big, right? It's a leak I can hear, I can see. It's quite drastic. It's big, it's bubbles, it's droplets. And then what we call emissions are things that we say are very small and difficult to see, to a point where we need an instrument to understand how much actually comes out. And one of the things that I've heard many times is actually the statement here. Helium leaks the fastest because it has the smallest molecule size. And that's wrong. And I brought a helium leak with me just to illustrate the idea. So I borrowed this from my nephew. I think you can imagine how old he is. And if I explain the theory that the molecule size plays a role in the ability to leak, I have to consider that this is sort of egg shape, that the ability to leak depends on basically the shape here. So it fits through, so it has potential to leak. Now this is slightly egg-shaped, so if I rotate it, it doesn't go through. Now I'm not sure what the shape of a helium molecule is. And I question if it's relevant. Because in reality, the gas is never stationary. Every molecule is actually moving in all directions. So the probability that the size of the molecule plays a role, whether it can actually pass through here, is near to none. Maybe at some point, like when we talked about absolutely leak-tight valves. So in reality, the things that play a role is the amplitude of the movement, because the further it moves, the smaller the probability it is that it would actually fit through the hole. Then there's the speed as well. So the faster it moves, the more probable it is that at some point it reaches that point and it leaks through. Now, simply said, the statement is wrong. So this is not the case, especially not in the magnitude of leaks that we're looking for. But the reason that we put this is that if I ask my nephew to solve this puzzle, what he will do, he will not bring the blocks and fit them through. He will simply take off the lid, solve the puzzle, and there we go. So it's not about the result, but it's about understanding what is going on. And this is just one myth about leakages, which is entirely wrong, but everyone will resonate this. If you're in a room with valve experts and you talk about what leaks faster, they will say helium, because of molecule size. And there are so many more myths. There's things like partial pressure. It plays a role, this and that, but it doesn't. It's all misconception. So when we talk about leakages, we have to understand the scale of leakage. So what I did, I draw a line here, and this is in units of 10 in the unit millibar liter per second, so the unit that we use for fugitive emission testing, from somewhere quite big to what we consider to be fugitive emissions here, and then the lower end of the spectrum what a mass spectrometer could theoretically measure. So if I then add some parameters, the relevance of the behavior of leakage is that, first of all, we have a concept called viscous flow, which is laminar and turbulent flow, for instance. I think we all know the principles because we're into valves. But there's also a transition point and a point where flow turns into molecular flow. And molecular flow is different in the sense that there is so much space between molecules that in theory, a molecule could leak in a different direction. which means that at the same time I can have leakage going outside and going inside, because the molecules don't collide, so they don't push the leakage outwards. So the transition point is actually quite important, and if we compare it to conventional testing, you can actually see that if you look at high pressure gas testing and hydrostatic testing, that there is a clear limitation to what you can actually measure, right? So the principle of those conventional tests would not allow you to do something like a fugitive emission test, simply because the measuring method isn't accurate enough. And it mostly relies on visuals, right? So it's droplets, it's bubbles, things like that. Then if we look at the spectrum for fugitive emissions, basically we're saying for level AH, BH, CH, this is the range where we're looking. So CH overlaps with high pressure gas testing, and what you can see is for level AH and BH, which is essentially here, there's a combination of molecular flow and viscous flow. So just for information, if we then add background, so helium background, for instance, is what I refer to as the amount of helium in the air here today. So there is helium in the air, and the level is just about here. So it's 1 times 10 to the minus 6, give or take. And that's why your criteria for fugitive emission testing based on sniffer method is 2 times 10 to the minus 6, because that's the first realistic measurement that you can take where you're above the background. And that's why this is what we call fugitive emissions. It's limited by measuring principle. Then looking at the criteria, so level AH, basically we're just outside the spectrum, but what you have to realize, obviously the criteria that we set is based on stem diameter multiplied by leakage criteria. So this is the starting point for each leak level, but in reality it's actually, it's a little further above in the line. So what people tend to forget is that every single step here is a factor of 10. So the gap between a level AH valve towards something you could test with high pressure gas testing is huge. The factor is enormous. It's really a different scale of testing. So going a level further, so if we zoom in, this is basically what we see as the realistic criteria for fugitive emission testing. And this is based on what you can find in ISO 15848. In the end, in Annex C, there is a table where they multiply stem diameter with leakage criteria, basically. So this is what we realistically expect. Then to go one step further into our criteria, if you read the standards, you can actually find that there's different methods of testing that you can do for testing of valves. And for instance, if you look at ISO 15848-1 for design validation, it holds all the descriptions of the test methods. And basically we have the vacuum method, where we eliminate background and then we are able to measure more accurately. We have the suck-through method, which essentially tries to eliminate a little bit of background, and then it allows a bit of accumulation, so it should be slightly more accurate, but it depends on how well you do the test, basically. And then finally we have the sniffing method, and the important thing here is that this is what we focused on in our research exclusively, because this is the method that you use for FAT testing. And practically it means that you have a sniffer and you measure by hand on the valve or by robot, like you saw in the video, and you accept that there is natural background. So you limit the measurability, but you accept that it's good enough for FAT testing. So now onwards to the relevance of viscous flow versus molecular flow. So step 1 for us was to determine what kind of flow can we expect. And the easiest way to do it is to just calculate it, because there is something called the Knudsen number. And the Knudsen number is something you can calculate, and it should give you an impression of whether it's molecular flow, viscous flow, or if it's a mixture of both. So what we did is we took some parameters based on valve standards, surface roughness, tolerances. We entered the data, and basically it tells us it's transitional flow, which is a bit of a shame, because transitional flow is undefined. It could be more molecular flow, could be more viscous flow. So we don't know, which means that we need to test. The interesting thing, though, is that if you look at the formulas that you would use for viscous flow, for instance, if you use laminar flow, which we presume is a fairly small leakage, so closer to fugitive emissions compared to turbulent flow, you can look at the formula, and then, because we're trying to compare helium with forming gas, we concluded that the only factor that plays a role on the magnitude of leakage, which is related to the gas, is viscosity. Which means that if I change the gas, then the factor determining how much comes out is viscosity. And if we then calculate theoretically what the transition is, so here, conversion factor for laminar flow from forming gas to helium is 0.89, which means that if I multiply my forming gas leak to helium, I multiply it by this factor, which means that my helium leak is actually less than my forming gas leak. And that shows great promise, because it means that there's good potential that you can use it for fugitive emission testing. But if you do the same for molecular flow, you find that the formula is very different, and instead of viscosity, molecular mass starts to play a role. And now it's interesting, because the molecular mass of forming gas, the average molecular mass, is much higher compared to that of helium. So what you see is that that same conversion factor here is actually a factor of 2.58, which means that if I would measure in forming gas, in reality my helium leak would leak more. So you can see that the behavior actually changes depending on what kind of flow you have. So establishing what kind of flow regime is relevant for FE testing determines the conversion factor between the gases. And if you compare different gases, you actually find the specific reason why the Americans like to test with methane. Because on the left here you can see the conversion factors for viscous flow. And what I've done, I've ordered them in which leaks the most. So you can see hydrogen leaks the most, then it's methane, nitrogen, air, and helium. So for viscous flow, helium is actually not a very good test medium because it will leak less compared to the other test mediums. And that's why the Americans, who have quite a high acceptable leak rate, they say you have to test with methane, because this is much closer to process conditions, and the gap here, so my conversion factor, I mean, it's 1 3/4 is the difference, so it's quite significant. But it all changes when you have molecular flow. So again, hydrogen is the worst, which I think everyone knows by now. I mean, it's been resonated in the industry for a very long time. And then we have helium as number 2. And then there's methane, nitrogen, air. So that flow regime that applies really has a big influence on how you should convert your leak rates if you want to switch to testing with forming gas. So fast forward to what we've done. So we did testing based on calibrated leaks, which means that we had leakage with a reference where we knew this is the amount of leakage that we can expect from this part, and we can validate that. So we can take a helium mass spectrometer and we can measure if we can actually achieve that value. And because it's a microcapillary, we can change the gas, so all the conditions remain exactly the same, temperatures, geometry. The only thing changing is the gas, and we can use the same instrument and different instruments to see how much comes out. And we did that in all the different magnitudes that we saw. So we said, worst case, we would have 1 × 10⁻⁷, which theoretically you cannot measure, and theory and practice align here because we couldn't measure. The next one is -6, -5, -4, -3. So we get the full spectrum to understand, is there a tipping point where the rules don't apply anymore? Because we want to provide a solution which adds to quality, not unnecessary costs or unnecessary incidents, quality defects in the field. So fast forward, what we found is that forming gas was actually a very good solution. Throughout the range that we tried to test, we found that we could prove the equivalent of helium and forming gas with just about the same effort. So it worked throughout the entire spectrum. So it's a viable alternative for helium, which is fantastic because the cost of gas is about 1/10 the price of helium. It all depends on your supplier, obviously, but it's the rule that applies to us. It's much cheaper to buy, and I can always buy it in the market. The side note is, though, that because we were working for Shell, we limited our research mainly to level AH and BH, because Shell always specify fugitive emission rated valve as level AH, BH, or not fugitive emission rated. And I'll get back to that later on. So a few of the things that we found, though, because this seems pretty straightforward. This is something you can just, you can buy these materials, you can do it yourself, you can do it in your workshop. But what we found is that stability is quite a tricky thing. And this emphasizes the importance of taking a reference point. Because we had calibrated leaks, so we knew how much leakage would have to come out of there. But to reproduce that exact value with helium was already quite challenging. It's not so easy as just put the probe on there and see what happens. No, you really have to take care in what you're doing. Even to a point where you have to say, okay, maybe I want to put the probe just above my leak and I want to step back a few meters because my presence, the fact that I'm moving, breathing, makes the air move around, which means that I cannot see my leak anymore. And the effect is super significant, and you don't realize it until you know what you're looking for. And that's the difference between testing with a valve. You don't know what comes out, and if you don't find anything, you presume it's good. But if you know there is a leak and you cannot find it, then what causes the problem? What causes it to hide from your detector? What we also found is that in the flow range that we're looking for, so again, based on Shell, we found that the dominant behavior is basically molecular flow, right? So the principle of laminar flow, it didn't really apply. So the range that we looked at specifically is the 10⁻⁶ to 10⁻⁴, because that's where AH, BH criteria would be, give or take. And because we saw some difference in measuring equipment, because we used different brand mass spectrometers, different brand hydrogen leak detectors, we settled on a slightly more conservative conversion factor, just to be sure. So the results are consistent, but because we don't want to cause issues, because we missed anything, we settled, let's take a slightly more conservative approach and write that into the standards. And the interesting thing about using different style detectors is that there is a huge difference in performance when you compare leak detectors. So the most common one that probably most of you have is a helium leak detector or helium mass spectrometer. It's basically the same device, different name. And there is simply a difference in construction. Some of them are built for vacuum systems, which means that they have an oil pump, because they need to draw a larger capacity of vacuum, and others don't. They're really built as sniffer devices. And their ability to measure is quite different, especially when you switch to forming gas, because forming gas is a mixture of hydrogen, 5%, combined with 95% nitrogen, which is inflammable, so there's no additional safety risk compared to testing with nitrogen. But the tracer component is hydrogen. And the thing that happens is that if your mass spectrometer has a tendency to draw a little bit of fumes from the oil pump, which most of them do, it actually shows up as background of hydrogen, because it will start to degas and it will start to influence the measurement that you have. So the alternative that we also had is that some brands of hydrogen leak detectors, which rely on a completely different principle, they work fine as well. And the interesting thing is that a mass spectrometer actually has moving parts, right? It has a vacuum pump, it sucks in air, and it has a maintenance interval, because it has moving parts. Hydrogen leak detectors are what they call diffusion sensors, which is a sandwich material from which you can measure diffusion of hydrogen on the surface. So the intelligence really lies in the tip. And actually what you see on the picture here, this is one of those hydrogen leak detectors. And this little bit here, this is actually the measuring device itself. The rest is just electronics and plastics to make it look good. And the interesting thing about that is that it's not 100% equivalent, the result that you get, but the difference is that it gives you a definitive result. So I introduce my probe, and it tells me this is the peak value that I saw. And in your mass spectrometer, you put the probe there, you have to wait for a while, you might see a peak come up, and then it goes down again, and then you move the probe a little bit, because we don't have very steady hands. So generally, we pick an average as the criterion. And if the inspector is in a bad mood, he will pick the highest peak, and if he's in a good mood, he will pick the lowest peak. You don't get that with hydrogen leak detectors. So from a perspective of being more user-friendly, it's just a nice to have, because it's, you know, touch and go. It tells me exactly what I need to know, and I can carry on. So another few things that play a role. So I talked about the difference in mass spectrometers. So there's a huge difference between brands and even between different models. Ironically, all mass spectrometers that we use in the valve industry, everything which is on the approved list from any international oil company, can be a completely different brand, but they are all built in the same factory, because there's only one factory that makes the internals of these leak detectors. And depending on the brand that you select, some companies have a tendency to work with vacuum. So they are vacuum companies. They provide vacuum pumps, they provide vacuum chambers. So their mass spectrometers are built for vacuum chambers because it's close to their product range. Others deal with semiconductors, and they don't really look at vacuum. It's not in their portfolio. So the sniffers that they have, they behave completely different. So one model could be excellent for both helium and forming gas, because it was built specifically for sniffing, and it's just a matter of setting it to measuring a different mass, recalibrating, and then you're good to go. Maybe you already have one. Maybe you can already set it to hydrogen, and then you could test with forming gas already. But others, they don't have that. They have that little bit of oil that plays a role, which means that if you turn on the device, the pump will start to run, and what you'll see in the screen is that the value that you measure is much higher than your natural background. Because theoretically, it should be in the range of 10 minus 7 for forming gas, for hydrogen, because that's the background level. But most of them actually start, when you just turn them on, in the range of 10 minus 3, which means that you cannot measure fugitive emissions with that device. And then you will call the manufacturer, and they will say, well, I mean, you can try to heat it up for a while. So after an hour, it goes to 10 minus 4. If you leave it on for 24 hours, maybe it goes to 10 minus 5. And if you're lucky enough, 48 hours later, then you're in the 10 minus 6. So now you can measure fugitive emission. But it means that you have to keep your mass spectrometer on all day, basically, which needs maintenance. So it's a terrible use case, basically. So that background is a key influence in your ability to measure. And it ultimately influences what brand and what model of mass spectrometer or hydrogen leak detector you can actually use. Now then there's another thing that plays a role, and that is what I would call surface area. So surface area, to me, if I have to explain it, I would use this picture from ISO 15848 to describe the sniffer method. And the idea about a mass spectrometer is that it has a vacuum pump and it draws in air, right? And then it analyzes the amount of air coming in, and depending on the amount of helium or hydrogen detected in that mixture, it will tell you this is the leak rate. So what happens is that if I have a big leak like I see here, I get quite a big amount of surface area from which I get helium or hydrogen being drawn into the device. So I actually measure from quite a big surface area here. And practically what it means is that if my emissions are quite high, so I have quite a big leak coming from my stem, automatically the device will give me a very high value because it takes it from a big surface area. And that sounds good because it's big leak, so it shows big value, so that's great, right? That's what I want. It gives me clear evidence, clear guidance. But if I have a small leak, then it's different. Because what happens is then here I have much less of my tracer gas, so much less helium or hydrogen. Which means that because my mass spectrometer draws in air with a fixed amount, it will dilute my leakage further. So the smaller my leak, the more difficult it gets to actually measure it. And that's a bit strange, because if you look at level AH levels, then this actually turns into quite a bit of a problem, especially if you consider that when I'm working close to my valve, I'm standing there, the influence is quite big, and the ability to measure really drops down quite significantly. So even if I put a window open, I might not be able to realistically achieve my leakage level there. So it's really something you have to take into account when you measure, that you get stable conditions and you use the right device for the right leakage level. And then there's a final conclusion, and this is perhaps an interesting one, and this is not very popular with the Americans, but what you see is that there is a transition point where the molecular flow turns into laminar flow. And it happens when leakage gets bigger. And if we compare helium with forming gas, that transition point between the two gases happens somewhere in the range of a level CH valve. And the thing that happens is that when you would measure with helium, you might feel that it's within the specified limit. So it seems like a fairly small leakage. But if you would change the gas to forming gas, or even nitrogen or air, it actually comes pouring out. It's actually very much leaking, because the helium will still act as molecular gas, molecular flow, whereas the other gas already transitioned into laminar flow, which means that it leaks much quicker. And that's very interesting, because it sort of discredits the idea of having a level CEH valve. And this is exactly the reason why Shell don't specify level CEH valves, because there's no point. The standard suggests you use helium for testing, which suggests that it's a very qualitative test. It gives you the impression that it's a very good thing to do because you can verify small leakages. But it's not the case. It's a false result, and it's expensive to do because of the gas and because of the test that you have to set up. Just a high pressure gas test would be much more effective for this. So fast forward, how do you use forming gas? First of all, if you work for Shell, basically they have a separate leakage criteria in their Shell depth. So it means that any valve which is fugitive emission tested for Shell, you're entirely free to use forming gas. There is specification, it's written, it's exactly what you need to do. There's a list of devices that you can use. They are approved by Shell. So you can do this already. The second one is for hydrogen valves according to API 6D, and they have similar requirements to Shell. The only difference is that API is obviously a manufacturer standard, so it's a democratic process. So Shell is practically a little bit more critical, right? They ask for a little bit more. So the test pressure is higher compared to the minimum in API 6D. And you know, Shell is a bit more explicit in the things that you need to follow. So if you're trying to set this up, my recommendation would be look at Shell, because they have the most elaborate standard for it. They will give you the most guidance, which means that if you can do Shell, you can also follow 6D Annex M. So the reason why it's only in Annex M is a matter of opportunity. So standards go through a revision cycle, and in the task group for Annex M, we had the authority to write specs for hydrogen valves, but you do not automatically get the authorization to change API 6D. But the idea about standards like API is that they take text which has been written, validated, and they copy it into the other standards. So at some point it moves all the way up, and all API standards will have this included. So it's a matter of time. And it's also a matter of time before it appears into ISO 15848-2, which is essentially the standard that would have the most impact. Again, it's a matter of revision cycle, so it's a matter of when does the task group come together to make changes, But the proposition is to include forming gas explicitly in that standard, because then all other standards don't need to follow that anymore, because API references ISO 15848-2, 1 and 2 by the way, but Shell does the same thing. So if it's in the ISO, it's basically everywhere. So 100% integration is still a matter of time, but I'd like to share what a principal engineer from GasUnie, which is a Dutch gas company, told me, because he followed the development quite closely. He was part of the API task group as well. And at some point he called me and said, well, I'd like to include this in our company standards as well, which is what they did. And at some point he told me, well, you know, the thing that I would like to do is I would like to tell each and every one of my suppliers that maybe if there's a particular valve that you still need to test with helium, still I will ask you to test everything instead of doing a high pressure gas test with nitrogen. You use forming gas. You use leak detectors to see if there's leakages, because then I have 100% quality assurance, and then maybe there is a few in the lot that you need to test with helium, but you know it's going to pass because you already tested it. And that forming gas test you can easily do in your own workshop, and for the 100% helium test you could easily go to a lab. And that's what they're specifying today for all of their hydrogen projects in the Netherlands. So all valves are being pre-tested with forming gas. And the reality is that if you pre-test, even if you test a cryogenic valve, if you follow the standard, it tells you that you need to do a test of the setup before you cool it down. And in every cryogenic test that we've done, we've tried to use a hydrogen leak detector before we would cool the valve. And generally we would find a little whiff, a little bit of a location where we would say, if it's going to leak, it's going to leak here. And every single valve that we tested, when we cooled it down, the point that we spotted with the hydrogen leak detector at ambient temperature was the exact spot where we had a leak at cryogenic temperature. So it's a powerful tool that you can use just as a practical tool to enhance quality and to make sure that if you're doing expensive testing, like testing with helium, testing cryogenics, that you can be sure that the quality, the result, is going to pass before you spend the resources, which could very well be finite resources. So that's the forming gas story in a nutshell, basically. Any questions? Any thoughts?
I understand you speak about the forming gas for cryogenic service, for cryogenic test. -1, -6.
So there's a bit of nuance there. I have to clarify. It's a good question. So the thing is that if you use forming gas in a cryogenic test and you go to -196, then the nitrogen portion would liquefy in the valve. So should you do it at cryogenic temperature? No. But the thing that we found is that if you pre-test the valve, so you're still at ambient temperature, you can do the test with forming gas rather than doing it with helium, and you'll find the probable location of leakages based on forming gas. So if there is a leak, you will know in advance, and then it's a decision up to you whether you still want to do the cryogenic test with helium. Because obviously the thing that happens is that the cryogenic test takes time, it takes liquid nitrogen, but it also takes that helium. And if it fails, you lose the helium, you lose the time, you lose the nitrogen. So it's a suggestion that for the pre-test you could use forming gas instead. And it gives you the assurance that if you do it, it will actually pass. Anyone else in the audience? Yeah, go ahead.
I'd like to know, for helium, usually we start measuring from the bottom of the valve,
Mm-hmm.
the leak path, and then we go up, no? Because the helium is lighter than the other gases. Okay.
Yeah.
Is this the same for hydrogen? The hydrogen has the same behavior.
It has about the same behavior. So the leakage will always accumulate. So let's say, you know, if I would have some geometry where it can sort of stick to, so maybe I have an actuator, it will always accumulate there. So it goes up. But the reality is that it behaves in sort of clouds, right? So your leakage will sort of form a cloud at one point, and the moment you introduce your probe, so with your mass spectrometer, actually you vacuum it away, so the clouds get less and less, so that's why you get a peak, and then it goes down. And if you come back again, if you're too fast, the peak is lower. If you're waiting long enough, you'll get the cloud again. And the behavior is actually quite similar with forming gas. But a key difference between forming gas and helium is that because forming gas only is 5% of the tracer, what happens is that if you have a fairly big leakage, and you would have it in helium, then it actually becomes more and more difficult to do your measurement, right? Because you get helium around the valve in the workshop. And if you have, let's say that your stamp packing fails, and you get a big release of helium, it could very well be that the rest of the day you struggle to do a measurement because your background is much higher. And it has to do with the gas being 100% concentration, which is what you need to be accurate with the gas. But with forming gas, you have that effect much less. So even if I would accidentally open up the bottle, I have a lot of echo, by the way. I guess you can hear the same. So if I would open up my bottle and I would just release gas into the room here, I mean, it's a huge contamination. And sure, it will affect my test results for a while. But it disperses so quickly because it's a lower concentration, and also the hydrogen has the tendency to disperse much quicker, that if I just open up a window for a while, I can go for lunch, and after lunch I can test again. So, especially with valves where you might suspect that they are going to fail, that you might have a leak, it's much easier to recover from that and then carry on testing again.
What about instead the temperatures? Because the production testing of ISO part 2 is about production testing.
Yeah.
But we also have to manage the prototype testing.
It's, again, a very good question.
So with high, elevated and low temperature testing.
Yeah. So,
hydrogen may be used also in elevated or low temperature testing as test fluid, or is there any danger?
Interesting question, and a very good question, because we haven't done that part of the research yet, because we focused on production testing mostly. So I can give you two answers. The first is 5% concentration at ambient temperature is not flammable. There is no way that I can light the gas. So it's the same as having nitrogen, basically. If the temperature goes up, then the acceptable percentage of hydrogen to be not flammable goes down. So, you know, maybe at 100 degrees, then it's 3% is the criteria, which means that it turns flammable. So you could say, well, then I cannot use it because it becomes flammable, which is a valid point. Helium doesn't have that, so I can always use helium for that. But if you look at the Americans again, they actually specify high temperature methane testing. Because if you talk to American laboratories, when they do testing based on methane, they say, well, sure, it's flammable. I mean, it's even flammable at ambient temperature. But the thing is that the testing we do is all based on small leakages. The testing we set up is based on that a very little bit comes out. It's not like we're going to have a big release of gas. We're not going to have catastrophic failure. So if you can do it with methane at high temperature, why shouldn't you be able to do it with forming gas? But the question here is, I mean, you could do it on a valve. You could just try. But there's a lot of different influences that will start to play a role. And when you look at design validation testing, basically you look at the total leakage or emission profile of a valve. So you have extended test times, you have extended test pressures, and basically what you're doing is you're setting up for what happens if I introduce pressure for a very long time. So the leakage you measure is a combination of sealing design, so performance of the seal to keep the leakage inside, but it also at some point starts to permeate through the material, which happens with helium. Then the process fluid could be completely different. But the leakage profile just is different. If you look at a production test, basically the only thing you're checking is, did I assemble it correctly? And is there anything wrong with the tolerances? Because the test time is shorter, and if you follow the ISO, I mean, test pressure is only 6 bars. Not if you work for IOCs, they specify higher test temperatures. But basically, it's a completely different test. So design validation, you could still do with helium. But the trick is that normally, unless you have a very big valve, it will still save you a lot of money, because in FAT you would consume the volume. And to put it in perspective, when we did supplier tryouts, basically, we found that the average expenditure on helium for production testing is around 30,000 euros per year in Northern Europe, give or take. So the perspective that for FAT you start using forming gas, it means that if it's 1/10 the cost, it's only 3,000 euros, which is a huge cost saving by introducing something fairly simple. So design validation is still a different subject, but good question.
I have a question about a specific type of valve, because I am from Carrara, we produce self-operated pressure regulators. I would like to know if you have any experience with testing fugitive emissions with pressure regulators across diaphragm, not just across stems.
Any shape or size we've done at some point. So
Also
yes.
Across the diaphragm, across the soft material.
Yes. So the interesting thing is that looking at the geometry, the question is how can we measure from the diaphragm, basically. So if you want to understand what goes through the diaphragm itself, so the material, the permeation, generally it makes more sense to do it as a separate test. So you do it in a fixture, because we also work with seal suppliers, and they do fugitive emission testing, but only on the seals, diaphragms, etc. And the nice thing about fixture testing is that you can create a very stable surface area, which means that as long as you can define that the seals keeping the diaphragm in place are working properly, you can only look at permeation through the material, which is essentially a different test. And if you look at the way we qualify designs, basically what you're saying is, seal manufacturer, I want you to look at permeation of the material, which is a subject they should look into. It's seal design, and both of them combined in the valve should have a minimal performance. And then the question is the valve design as such that the seal design works in the valve as well? So if you look at every single step related to fugitive emission testing, there's actually many more steps to go through, because the seal you qualify separately. And the only thing you would check in your valve is to check if the assembly is according to your design. So there are separate standards, and I don't know the number by heart, but there's a new...
What are the standards that you have received the request, if you have? If you have received some request according to some standard to do you?
Everyone nowadays just says we want ISO 15848, or it's an international oil company, so it's, you know, Aramco spec, it's Shell spec, Gasunie spec, whatever. And that's the majority portion, and then the follow-up question is always, what about hydrogen valves, basically, which is essentially the same answer, because we use a reference to ISO instead. But if you really want to look at seal material, I would say, I'd have to look up the numbers, I don't know them by heart, but I think ISO released a separate standard for at least seal qualifications for stem seals, and there's different standards to qualify seal materials and seal design for stem seals. So it's ultimately the test procedure is not so different, but they talk about how the fixture should be made and how you verify it in the test procedure. Send me an email and I'll send you the numbers. Anyone else with a question? Okay. I just need a bit more of your attention. It's almost done for today, but I kept perhaps the most interesting subject for last, because I think this is a concept that I've been getting questions about this for, well, at least the 8 years that I worked at Ventil. How can we achieve this? How can we do testing at minus 250 degrees Celsius? And I fully recognize that the market for liquid hydrogen valves is still quite a low market. So it's really something for the future. But we think we have the solution. We think this is going to be the future of testing at what we call deep cryogenic testing. And the slide style changes because this is in a different phase. This is a phase where we say we have the solution, and we feel that if liquid hydrogen ever starts, we have the way to go. But the question is, when is the market ready to accept this as a method? Because there's no demand yet. So when do we build the prototype, right? We can do it today, then it costs a lot of money. But if you don't need it until, well, maybe 10 years, there's no point. So that's why this is what I would say an innovation plan. So let me run you through it. Quite simply said, our mission here is to facilitate testing of liquid hydrogen valves. We've been getting the question for a very long time, and we've looked into all technical options. We've done prototype designs, we've done proof of concepts, and we've been looking into market situation. And our purpose is to build a prototype for cryogenic testing all the way down to minus 253. What we call deep cryogenic testing, because it's below conventional cryogenic testing. And the target is really that minus 253. The reason that we're doing this is that we believe that it's very well possible that testing with liquid nitrogen for liquid hydrogen applications is simply not enough. And if there is a use case, if there is a business case for liquid hydrogen, it means that safety and reliability will be key factors for those projects to succeed. So the vision that we have is that we're trying to solve a missing link here, because there is very little ways how you can test a valve at minus 253. So we really see this as one of the missing links when it comes to pressure test benches, so the business that I am in today. And I could build a proof of concept, right? I could do this on a small scale, I could have it on the desk here, and I can prove to you I can reach these temperatures. Because the reality is that humankind has been able to reach the absolute 0 point within 1/1000th of a degree, which means that we have technical capability to reach those extremely cold temperatures to a point where it's physically impossible to go below that. But it's all at a very small scale. So then it doesn't make sense, because the energy industry where we're in, everything is big. So we need to look at scale. And the reality about building a prototype is that now we don't know what the factors are that we need to take into account. So everything we learn along the way before liquid hydrogen is actually commercialized will be input to improve economic viability of liquid hydrogen. Because if you buy components, if you sell components which will last much longer, it means that the business case for the energy major is much better, because maintenance costs money, period. And quite lovingly, I'd like to call this the cryo conundrum. And it's sort of the counter-opposing things about cryogenics. Because the tendency is that cryogenics is good enough. Liquid nitrogen is good enough if you are producing liquid hydrogen valves. But in reality, if you look at the difference in temperature between liquid nitrogen, minus 196, and minus 253, the temperature of liquid hydrogen, it's about the same temperature difference as being in the Arctic or being in the Mediterranean in winter. The temperature difference is huge. As a human being, you would dress differently. You would not easily survive in the Arctic, but you would be comfortable in the Mediterranean, basically. And the temperature difference is quite huge. And what we don't seem to realize is that if you look at leakage of gases, so emissions and leakages, actually at those cold temperatures, the effect is at its absolute worst because of the physical properties of the gases and the fluids inside the pipeline. So the relevance is simply that we need to know if it's good enough, which means that we need to do some sort of testing to know what we need to do to establish minimal quality for valves. And then in the conundrum, what we also see is that size matters, because liquid hydrogen valves have been around. It's rocket fuel. It's used in scientific applications. We even have liquid helium valves, because superconductors are cooled with liquid helium. But the reality is that all of those valves have a completely different operating profile and size compared to what we would do in the energy industry. Because rockets are not fired into space every day, right? So the valves are not used so often. And the amount of energy that you put into a rocket, sure, is a lot of energy, but you're not in a rush. But if you're trying to transport energy from Australia to Europe, for instance, then you are in a rush, because the longer it takes to fill your carrier, the more time you lose, the more money you lose. So size is a very big factor in this conundrum, which means that those small valves that we have today, sure, they will work, but are they enough? Is it good enough for a liquid hydrogen economy? And obviously, the market is not there yet, right? So if you talk to an energy company, they will say there's no business case for hydrogen, so there's no business case for liquid hydrogen. But the reality is that we're technocratic. And technocratic to me means that we're ever developing new technologies to a point where we can successfully implement them in a commercial way. So there will be a point in the future where liquid hydrogen will have a commercial purpose. Now, I cannot predict the future, unfortunately not, but I do see three main use cases where liquid hydrogen could be used. And the first one is large-scale transportation. And there is a liquid hydrogen vessel. It was developed in Japan. It sailed to Australia. It was filled up with liquid hydrogen. It sailed to Japan. And apparently it was a big success, but no one published any results, which is not a great sign, usually. And then you don't really read anything about it in the news, which is not a great sign, until I found that the ship is actually occasionally going on a world tour. So just to see if they can bunker up fuel in different places, the ship is actually being used just to try out how it behaves. And actually they're developing a new ship because they figured they had lessons learned. So something is happening there. And it's the same thing for marine fuel. So container ships could run on liquid hydrogen. And there's actually projects being developed to investigate, can we provide liquid hydrogen for shipping instead of just bunker fuel, which is horrible for the environment because it's the heaviest crude you can get. And then finally, perhaps the most interesting, which perhaps is going to be the quickest one to get off the ground, and that's an intended joke, is aviation. Because especially for short-haul flights, it's not unthinkable, in fact, Airbus is developing this, that all domestic flights within Europe will fly on liquid hydrogen, which means that next time when I try to fly here, I could fly on liquid hydrogen. And aviation is obviously a big market. But how far along are we, right? So, I mean, this is looking into the future, and you know, maybe you believe me, maybe you don't. So what do you look for in the market to understand if we're ever evolving into this? Is it really going to happen? Well, three projects which are interesting, which I always use to explain relevance of this project for us. First of all, we know that Shell was one of the sponsors of that first liquid hydrogen carrier. They're not very open about it, but if you read the news, you can actually see that they funded it. And actually in the news, you can also find that they have started a development project, however quick it might go, to create a second liquid hydrogen carrier. And one of the challenges is, how do I keep liquid hydrogen inside that tank without too much energy loss? And in the news, project number 1, they actually developed a storage tank with insulation which is not solely based on vacuum. Because the problem with vacuum tanks is that if I get a compromise in vacuum and I get air sucked into my vacuum, the air is actually supercooled, which means that the components will actually start to liquefy and freeze. And as it heats up, I might just get a flammable or explosive mixture in my vacuum jacket, which means that if anything happens, if there is the slightest bit of spark, everything would blow up. So having a different concept to insulate is one of the key factors to make the technology work on a commercial scale. So something is happening in the market. A second thing, quite interesting, was quite a big thing in the news in the Netherlands, is that the Sultan of Oman came to the Netherlands to talk about a liquid hydrogen corridor between Oman and the port of Amsterdam. And if you analyze it, then maybe there's not a business case for hydrogen, because in my house I don't want to have hydrogen because I have solar panels, so it's not interesting. But we do have a very strong presence of steel industry in Western Europe, in the sense that we have close to Amsterdam. The port of Amsterdam is a steel mill, and we're working on a hydrogen network all the way going into Germany, into what we call the Ruhrgebiet, where all the steel plants in Germany are. And they rely heavily on hydrogen to produce green steel. So supply and demand is settling there, where Oman is saying we can produce green hydrogen and we can export it to the Netherlands and then through the Netherlands into Germany in the form of liquid hydrogen. It's an early phase, but it's a development. And then finally, our airport, Schiphol, announced collaboration projects with different airports to prepare for liquid hydrogen at airfields. Because if you look at the development for liquid hydrogen in aviation, the interesting thing is that Airbus claims that if they want to, they can have an aircraft that solely flies on liquid hydrogen by 2030. And that's not so far away, in my opinion. But what they signal as the main issue for liquid hydrogen in aviation is the ability to do ground handling with liquid hydrogen. In other words, the logistics at the airfield and how do we get liquid hydrogen to the airfield so we can fuel up aircraft. It's a bigger problem than the ability to create an aircraft to fly. So supply and demand has to find its way. Once the aircraft is there, it has to find its way. So if you look at liquid hydrogen in the industry today, what you see is that we use the energy transition as the blueprint, right? This is our main reason to do it. We want to decarbonize. This is what we're trying to achieve. And hydrogen plays a role in that. So it's not a form of energy, but it's a way to transport and store energy. So that liquid, the hydrogen transition, basically it has to find its way. And the only way forward is to increase scale. And ultimately, if we speak to energy companies, they say, our ultimate business case is based on 16 to 20-inch pipelines. Then it's the most effective part, the most effective size for us to be commercial. But we need supply and demand, and we need technology to be proven, which means that today it's about what I would call the mid-range, which is much smaller, but the pipeline size is 6 to 8 inch, give or take. So anything which is considered to be a pilot project for, I would say, the next 5 years, is all based on 6 to 8 inch pipelines, with the tendency to go bigger in the future. And then if you speak about what's the challenge here, because I mean there's liquid hydrogen valves, so why don't you just buy liquid hydrogen valves and Don't we have it already? And then the question is reliability. So in the case of that vessel in Australia being filled with liquid hydrogen and it needs to sail to a different location to unload, what they say is that, first of all, the challenge is that the components are too small, so bunkering takes too long. LNG you can bunker in a day, hydrogen takes a week. It's too long, so we need to upscale. Everything needs to be bigger. But the bigger problem is that once you do that cycle of bunkering, and you repeat it a couple of times, after about 5, 6, 7 bunker cycles, which is not a lot, so filling 7 boats, components start to fail. And it has to do with that thermal contraction of the material. So the reliability of the components is not there yet, that you can have a facility that can run for years without significant maintenance, because the components start to break in the meantime. And that's a limitation in the business case. Because if you want to sell something as cheap as hydrogen, you need to make sure that you have everything in order to keep your cost down. Because it doesn't sell at a high price, period. So reliability is a key step to develop technologies like liquid hydrogen. Now, if we look at a more technical scale, why does it matter that -253? Why is it such a big deal? Then there's a few different arguments that you can give. The number one is thermal stress. It's contraction. As you cool down, you will have stress in the material. You could have loss of pretension of components. You could have microchannels opening up because of that tension, which could worsen over time. So the more cycles you go through, the more of an issue it turns into. But it's also things like cold welding of components together, because the conditions at those very cold temperatures actually result in lower allowable contact stress before something is cold welded together. And the effect is worsened when you put liquid hydrogen in the system, because it can very well remove oxide layers from steel materials, which means that that contact stress is reduced even further, which means that components that perfectly work at -196, they could be stuck together when they have had a couple of thermal cycles at -253. Then if you look at, for instance, the difference in contraction. So obviously if I take a piece of stainless steel pipe and I reduce temperature by submerging it in liquid nitrogen, then it shrinks, right? It's a concept that we all know. So to go even lower in temperature, so the difference between liquid nitrogen and liquid hydrogen, per meter of length of pipe, I have an additional 0.2 millimeter crimp, which means that my pipe is 0.2 millimeters shorter, extra. And that may not seem like much, but if you look at tolerances in your machining, then it's quite a significant number, especially if you go bigger in valves. So more material, more contraction, more deviation. But it actually gets worse, because I mean, looking at those numbers, it's not very compelling, right? It's a difference, but I mean, what's really the difference? But what people don't realize about these temperatures is that we feel that stainless steel is a very good conductor. Don't you agree? So if I put my hand on a stainless steel table, I can feel the cold, which means that there is temperature differential. And probably you have stainless steel pans in restaurants, in homes, because they're good conductors. But if you reduce the temperature enough, and that happens once you go below that liquid nitrogen temperature, it actually turns into an insulator. And that's a bit strange. So if you look at space applications, for instance, where they go to outer space temperature, so very close to the absolute zero, they use stainless steel as insulators. Which means that if you look at my temperature profile here, basically what I try to do is simulate temperature over a length of pipe. So imagine 2-inch pipe, 1 meter in length, or think half a meter in length. And I simulate the temperature every 100 millimeter. And let's presume that all of my cooling power comes from the left end, so from this side. It means that I get a temperature gradient over the pipe, which is quite logical. And what we fail to realize is that because the material becomes an insulator, the limiting factor is not cooling power, but it's the ability for the material to conduct heat to a particular point. So if I have a valve which is entirely closed and there's liquid hydrogen on one side, I will have a huge temperature gradient over a huge amount of time on the other side because the heat is so slowly being drawn through the material. So in the simulation here, just to illustrate, so every single line represents an increment in the length. So the yellow line here is 0 millimeter, this is 100 millimeter, etc., etc., etc. Right? So you can see there's a temperature curve, and it's quite a steep one. So if I would cool this for, well, let's say it's close to 10 hours, my 0 point could be minus 253, but then at 100 millimeter, I'm at liquid nitrogen temperature. So I have a huge difference in temperature that would occur in the field as well. And it doesn't have anything to do with cooling power, contact surface of liquid hydrogen inside the valve. It's solely restricted by the stainless steel becoming an insulator along the way. And it's a huge concern because if I would bunker a boat for a week, it means that my temperature gradient throughout my installation will be continuously changing and could be very much worsening, which means that I have to compensate for that in my design. So it's not just thermal contraction, it's thermal contraction over time, temperature differences, etc. And this is a huge question mark, because every single test that we've done, even if you look at applications like space applications, the duration where liquid hydrogen is introduced into components like valves is fairly short compared to if I would need to bunker a boat for a week. And that's why reliability becomes a concern, because you don't know how the valve will perform, or the swivel, or the pipeline, etc., etc. So let's look at key technologies to facilitate this test. Because ultimately we just want to know, right? If we do a test, we know. And then if we know, we can decide what we have to do as an industry. We can write our standards, we can prepare, and we can make this into a success. So the first technology is to cool in a reservoir. And the main limitation is that you need to have a coolant which is able to reach at minus 253 degrees Celsius. And that leaves you with two options. The first is liquid hydrogen, which is very flammable, which means that's probably quite impractical to have in your facility. Also, you would have to get the liquid hydrogen from somewhere, which is a challenge nowadays, because production is not very big there. The second alternative is liquid helium, but liquid helium is very expensive, and there's only very few places in Europe and the US where you can actually get liquid helium. And there is actually a story of manufacturers that rely on liquid helium, that they have reoccurring cycles where if they need to get liquid helium, that they have to fight for their right to receive liquid helium, to a point where the truck could be on the way to their factory and they get a call and they turn around because something else is more important. So it's not a very sustainable way, considering that this could be a solution to our energy problem, which means that there's going to be a big volume of valves. If everyone needs liquid helium, it's simply not going to work. So the other option is to go with flow-through, which essentially I mount the valve into a pipeline and I run liquid hydrogen or liquid helium through it. Because ultimately this could be close to the operating profile that I have in mind, which means that I cool it down by just introducing the liquid inside the valve. So it will cool down, but the reality is that it's a fairly expensive thing to do, because the installation that you need is quite big, and it's probably what they have at space agencies, which is a fairly expensive test to do, because we asked around how much would it cost to do a test like this, and it's expensive. So it doesn't seem like a great way to go, mostly because if we cool it down to that temperature, we don't really have the measuring conditions to be able to measure in an accurate way. Because if we talk about fugitive emissions, for instance, I would not really be able to do my qualification test on the stem or the body or whatever, because the liquid I use for cooling is also the tracer that I want to use for leak detection. And then if I decide that I cool it and I take it out, then I will never be at -253 because it will heat up over time. So it brings some concerns about, can I even achieve that temperature range? Because it's impractical, period. And that leads us to the third option, and I think you can hear it coming. This is what we're aiming for, and it's based on conduction, basically. So we're not using liquids for cooling, but we want to draw heat from the material using conduction. So just to tease you, we believe that this is the best solution, what we call deep cryogenic testing, and it's inspired by technologies used in the space industry, basically. And the idea is that we use cryogenic coolers, which only consume electric power, and through conduction from the material, we draw heat out of there until the moment that we reach a temperature that we want to achieve. So it's controllable. We don't need any technical gases or fluids to achieve that temperature. And we can do pressure testing based on helium and even on liquid hydrogen. So we're not using it for cooling, we're using it for testing instead, because we can create stable measuring conditions. And the idea is that because we have a controllable process, we can use it for the typical testing we want to do for design validation, which is mechanical cycles, temperature cycles, and pressure cycles. So it should be very manageable. And the key thing here, again, is size. It's about scale. So we've been trying to figure out what will happen in the next 5 years, and that's how we came to the 6 to 8 inch pipeline. And the joke is that no one has that design of valve ready. So we had to do a best guesstimate. So we said, let's aim for an energy model, so our prototype based on a 6 inch valve. So we need a particular envelope in which we can put the valve. And let's say that the maximum mass is about 200 kilograms. And let's say that we want to cool it down in 24 hours. Those are the parameters that we're trying to follow. Then if we compare the different technologies, because obviously you have to make, for a good business case, a good comparison, basically what we see is that conduction cooling has fairly low operating costs, because we only consume electric power, but the capital expenditure is quite high. And it mostly has to do today with the fact that we don't know what it takes. Small scale, large scale is a completely different story. So it seems that the investment cost is fairly high today, but it could very well be that once the technology matures, that it's actually a competitive method compared to using liquid nitrogen to use to reach -196 degrees Celsius. So we don't rely on technical fluids and gases because it's just electric power. The only thing we would use is helium and liquid hydrogen for testing itself. So it's the test medium, which means that the consumption is less. We can maintain a -253 degrees Celsius. We can test uninterrupted without limitation. There's no limit to how long you can test. And the measuring environment is controlled. So we can measure very accurately what external and internal leakage would do inside the valve at any given stage, during cooling and at cold temperature, mechanical cycles, pressure cycles, etc. And the other methods, they tend to have high operating costs because of those technical fluids, right? Is either that, because we have to purchase it and it's limited availability, or it has to do with the infrastructure that we need to make it or maintain it. Creating your own liquid hydrogen, creating your own liquid helium is just very expensive, period. Also, we see issues with the measurements that we want to do, because we would rely on coolants, which are also our tracers. And you could say, you could think helium and hydrogen are separate matter. So if I cool with one and I test with the other, that should go. But that's not the case. because your helium or hydrogen leak detector is never insensitive to the other medium, which means that it gets polluted if there is a high concentration of the other substance. So if I measure based on helium, but I have a high concentration of hydrogen, the masses of the molecules are so close that it influences my test result, making the test essentially useless. So how it works. We intend to use cryocoolers, and they will be optimized for the temperature range that we need to achieve. In cryocoolers, I have a next sheet to explain a little bit more. I'd like to compare it to a fridge. If I have to tell my wife this is how it works, I tell her, you know, we have a fridge and it has a compressor and an expander. What happens is we compress a coolant, and when it expands, we draw heat from the environment. And in our fridge, we cool the air, and the air is in contact with my beer, and then after a while, my beer is cold and I'm happy. I can recompress my coolant, which means that I have a continuous cycle going on. There is coolers that can actually achieve these temperatures, but they really have to be optimized for cooling because they are never designed for use cases like this. The combination of size and mass is quite a challenge for the suppliers of these materials. So there is nothing available in the market today which will give you flying colors, basically. You know, there is still some developments to do there. Then also what you need to consider is that the cooling capacity is fairly limited, which means that if we want to be quick and achieve our 24-hour time span, we have to consider that we might want to have higher temperature coolers for the first stage of cooling, and then thermally switching them off, and then going to a lower stage cooler. And it goes to a point where if you don't have thermal switches and thermal connections which are optimized, you will never reach that temperature. So again, it's something to really consider in the design, which all depends on scale of the solution. So the intention is to always start with high pressure gas testing based on helium, because it gives you a profile whether the valve is actually leak tight. So it gives you an impression whether it will catastrophically fail, yes or no, basically. Once you know that the profile is good, so you know that it's leak tight and it's reasonable to presume that it will not fail, in the same concept, you can actually test with liquid hydrogen as well. But again, you don't use it for cooling, you just use it as the test fluid. So you can operate at, or you can simulate operating conditions inside the test bench. You would also be able to open and close the test object at cold temperature, and any temperature between ambient and cold temperature. And it will all be placed inside this vacuum chamber. And this is about the scale that we would need for the 6-inch valve. So the idea is that the vacuum chamber is used to insulate all heat input to compensate for the low capacity of the coolers, which means that vacuum eliminates convection because there's no air. At the same time, it gives us the opportunity to do external leak testing, because if there's a vacuum chamber, we can connect a leak detector, right? And we'll take one which is optimized for vacuum because it will outperform the others. All thermal connections, obviously, we want to optimize to a point that the valve is being cooled by its support. So we manufacture a method or a fixture in which we make our thermal connections to specific points on the valve body, and they directly connect to the coolers, which means that the structure inside is all cooling structure. And then finally, if you look at thermodynamics, we're left with radiation. So once you cool down, you'll see that radiation will actually heat up the valve quite a bit. So it means that we would cover the insides of the vacuum chamber with a pre-cooled radiation shield to make sure that the effect of radiation is as little as possible. And by doing so, we can simulate a situation which could happen in the field. You know, it's sunshine, it's warm weather, cold weather, etc. But we do everything at a smaller scale because our cooling power is a bit limited. But it's a very manageable process. And just to clarify how that cooling works. So if I compare my fridge to, well, the main principle that we intend to use is a Gifford-McMahon cooler. And it's a principle which has been developed a very long time ago, and it's a regenerative cooling process. So the principle is that you use helium for cooling, so you compress it and you let it expand, from which it draws heat from the environment. But to reach those cold temperatures, you have to pre-cool the gas, which means that the compressed gas needs to be cooled. Then you allow it to expand, and in a sort of continuous process, it will get colder and colder and colder. So what happens in the picture here is basically the gas travels through the components, through the displacer, and this is the first stage of heat transfer. It travels further to a second stage of heat transfer. So once it's expanded, what we do is we move the displacer down. So these components here, they actually move down and they push the expanded gas back to the outside. So not like your fridge where it's a continuous process where the compressor is continuously running, basically. This is a cycle process. So it's gas in, gas out. And as it goes on, the temperature goes down. If you look at the design of these in the market, you can always find that there is, as a rule of thumb, there's 4K and 20K coolers. And the 4 and 20K refers to temperature, but not in degrees Celsius, but in Kelvin. So 20 Kelvin is -253, give or take. And the trick with that is that a 20K cooler has a much higher capacity compared to a 4K cooler, but a 20K cooler is not enough to get my test object at -253, because there will always be thermal loss over the length of the body. So it means that if I want to reach -253, I have to have cooling capacity lower than what I'm trying to achieve. So you will always have a mixture of fairly high capacity 20K coolers, which are optimized for a big mass, and then thermally switching to 4K coolers with a lower capacity. And this sounds a bit counterintuitive, but that effective insulation of the stainless steel is actually the limitation. So what you see if you take a thin-walled pipe, it will take longer to cool than a thick-walled pipe with a much higher mass, because of the ability of the heat to transfer throughout the material. So it's really something that needs to be optimized, and you need to be aware of it. It's not like we just add more power and then it will go well. No, you have to engineer this, you have to consider this, and you need to have a stable solution for, or at least that 6 to 8 inch valve. Ultimately, what it comes down to is the cost of cooling. So the energy cost it would take to cool our 200 kilo from ambient temperature to -25 degrees Celsius is 300 euros, which is nothing. Every time we do a cryogenic test, and we don't have a facility for liquid nitrogen, right? So we have to get an external supplier. This is 10 times cheaper than getting a truck of liquid nitrogen for us. So the energy consumption is extremely low. So the only challenge is what do we do with the investment cost? And now we're at chicken and egg, because if there's no business case, no one's buying liquid hydrogen valves, what do we do? Do we wait until someone says we're willing to go forward, or do we do it differently? And we'd like to do things differently, because that's the nature of Ventil. We'd like to be ahead, have the initiative, which means that we're actively seeking out partners to develop this prototype. And our main goal is to get energy companies to buy into this, because if there is a moment where liquid hydrogen has potential in the market to be sold, so there's supply and demand and there is a market price for it, we'd like to be ahead of that. Because otherwise we would wait until there's supply and demand, and then we have to develop everything. So we're actively reaching out to end users in Western Europe and in the Middle East, because Western Europe is the place where we believe we're going to consume, and the Middle East is a key region where green hydrogen is developed, either as greenwashing or as a good business case. It doesn't matter. So there is interest there. And the idea is that we're focusing for now, because this is market intelligence that we've been getting, that the valve has to fit in a 2x1x2 chamber. The cooling mass is 200 kilograms. We want to cool it in 24 hours. And we want to do external and internal leak testing, primarily based on helium and liquid hydrogen. So again, I can't look into the future, but with the discussions we've been having, this is the timeline that we're looking at to develop this. So we have interested end users, but they're hesitant because there's no business case. So the idea is that we focus the rest of the year on defining the scale that they need to achieve for their potential mid-range prototype. And early next year, we want to launch a project. So we want to find partnerships to collaborate, do our final thermal simulations to ensure that the prototype design actually works, and then manufacture it before the end of the year. So hopefully around this time next year, I'm not talking about simulations on temperature of valves or pipes, but then we actually have data on a valve being cooled to -253 degrees Celsius. And again, what I started with this morning, we believe that at Ventil, we're a small company, right? If we're talking about subjects like these. But it's the insight that we get from testing and understanding how things like leakages, cooling processes work, where we feel that we can contribute to a better world, to bring us closer to the technologies that we need tomorrow. So this is, for us, a big part of our mission to contribute to the valve industry and do our part. And with that being said, I think it concludes today's training session on, I think, a wide variety of subjects. I'd like to thank Virginia for having me. Wonderful. So a big round of applause for her, please, because she did absolutely great. And then finally, also a big thanks to you, Oscar, because we mentioned this, but Oscar was kind enough to invite me here for these days of training. So it's been absolutely fantastic, and it's been my honor to be here today. Thank you very much for your attention. Do you want to close up? Then I have a final slide. I think you should be a member of VALVEcampus because, I think you can benefit from sharing knowledge, events like these, and I just hope you have a great time today. Thank you very much. And I will take questions, by the way, if you want.